Please subscribe to support the channel. Quasars are among the most extraordinary discoveries in astronomy, and even today, they remain objects that challenge both our imagination and our scientific understanding. To introduce them properly, let's start with the most striking fact. Quasars are some of the brightest objects in the universe. When astronomers first stumbled upon them, they were shocked, because here were objects that outshone entire galaxies, yet in the sky, they looked no larger than a single star. That paradox alone is enough to spark curiosity. How could a point of light rival the combined brilliance of billions of suns? The word quasar carries a certain mystique, but to appreciate just how strange and powerful these objects are, one needs to break down the phenomenon at its heart. A quasar is not a star, nor is it a galaxy in the ordinary sense. Instead, a quasar is what happens when a supermassive black hole at the center of a galaxy begins devouring matter at a furious pace. As this matter falls inward, it doesn't simply vanish into darkness. Instead, before crossing the event horizon, it forms a swirling accretion disk, an inferno of gas, dust, and radiation. The friction and compression in this disk heat the material to unimaginable temperatures, releasing energy across the electromagnetic spectrum. The result is a beacon so luminous that it can be seen across billions of light-years. To put this into perspective, a typical quasar can emit hundreds or even thousands of times the energy of our Milky Way galaxy, all from a region not much larger than our solar system. The contrast is mind-bending. Here on Earth, our Sun is the dominant source of energy and light for our planet. Yet quasars like 3C273 emit energy that dwarfs the combined output of every single star in a galaxy of hundreds of billions of suns. This is why astronomers often describe quasars as lighthouses of the cosmos. But brightness alone isn't what makes quasars so important. They're also cosmic time machines. Because they are visible from such enormous distances, observing a quasar means looking back in time, to an era when the universe was much younger. Some quasars we see today were already blazing when the universe was just a fraction of its current age. This makes them not only spectacular in their own right but also essential probes of cosmic history. Through them, astronomers study how galaxies and black holes grew together, how the early universe evolved, and how the large-scale structure of the cosmos came to be. Quasars are also versatile. They emit energy across the entire electromagnetic spectrum: radio waves, visible light, ultraviolet, X-rays, and even gamma rays. This multi-wavelength character makes them laboratories for extreme physics, from relativity to plasma dynamics. The jets that some quasars shoot out at nearly the speed of light offer further puzzles, providing glimpses into processes that no laboratory on Earth could replicate. The awe they inspire is universal. For scientists, quasars are crucial keys to understanding cosmology. For the general public, they represent the sheer majesty and scale of the universe, a reminder that beyond the familiar stars we see at night lies a cosmos teeming with energies and phenomena beyond ordinary comprehension. And when we talk about the first quasar to be identified, 3C273, we're not just talking about an object. We're talking about a turning point in astronomy. Its discovery marked a moment when humanity's vision of the universe expanded dramatically. So, at its core, a quasar is a paradoxical beacon, a pinpoint of light that masquerades as a star, yet secretly reveals the presence of a supermassive black hole unleashing unimaginable energy. To introduce quasars is to introduce a frontier of astronomy where ordinary categories break down, and where the very scale of cosmic power becomes difficult to grasp. They are brilliant, distant, ancient, and endlessly fascinating. The kinds of objects that remind us how small we are and how vast the universe truly is. At the dawn of the 20th century, astronomy stood at a fascinating crossroads. The great discoveries of the 19th century, spectroscopy, photography, and the recognition that the Milky Way was but one galaxy among countless others, had already transformed the way humanity thought about the universe. Yet, for all the progress made in optical astronomy, the story of the cosmos was far from complete. Astronomers were still limited by the light their telescopes could gather through lenses and mirrors, and the electromagnetic spectrum remained, for the most part, unexplored. To put it simply, the cosmos was speaking in many voices, but humanity could only hear one. It was in this context that a revolution began, slowly at first, then gathering momentum: the rise of radio astronomy. Radio waves had been studied since the late 19th century, with Heinrich Hertz first demonstrating their existence in the 1880s. By the early 20th century, pioneers like Guglielmo Marconi had harnessed radio for communication across the Atlantic, and it became a vital technology for ships, airplanes, and later warfare. But hardly anyone suspected that the heavens themselves might be broadcasting radio signals. Telescopes of the time were still focused on visible light, and the idea that stars or galaxies could be radio loud had not yet entered scientific thought. Astronomy was rooted in optical tradition, peering through glass lenses at stars and nebulae, recording faint glimmers on photographic plates. The turning point came in the 1930s with an engineer named Carl Jansky. Working at Bell Telephone Laboratories, Jansky was tasked with investigating sources of static that interfered with transatlantic radio communications. What he stumbled upon was astonishing, a faint but consistent hiss of radio noise that seemed to come from the sky, not from Earth. After carefully analyzing its cycle, he realized it repeated every sidereal day, the exact length of time it takes for the Earth to rotate relative to the stars, not the Sun. This meant the source of the noise was cosmic. Jansky had, without realizing it, discovered the radio universe. Despite the significance of Jansky's finding, the astronomical community was slow to embrace it. In the 1930s and 1940s, funding and attention were directed toward the development of radar technology during World War II. But radar would, ironically, lay the groundwork for the new science of radio astronomy. After the war, scientists repurposed radar dishes and equipment to build the first dedicated radio telescopes. One of these early pioneers was Grote Reber, a radio engineer who built a parabolic dish antenna in his backyard in Illinois. Reber systematically mapped the sky in radio wavelengths, confirming Jansky's discovery and showing that the Milky Way itself was glowing with radio emissions. These early efforts were the seeds of a revolution. By the mid-20th century, as larger and more sensitive radio dishes came online, astronomers began cataloging mysterious new sources of radio emissions scattered across the sky. Unlike stars and galaxies familiar from optical telescopes, these radio sources often had no obvious counterparts in visible light. They were puzzling, enigmatic, and sometimes frustrating. What could be producing such strong radio signals? Were they exotic stars? Supernova remnants? Entire galaxies in some unusual state? Nobody was sure. In the early 1950s and 1960s, projects like the Cambridge surveys in England took on the ambitious task of systematically mapping these sources. Using arrays of radio antennas, astronomers began to compile catalogues of hundreds, then thousands, of radio emitters. One of the most famous of these was the third Cambridge catalogue of radio sources, known simply as 3C. Each entry in this catalogue represented an object that shone brightly in radio wavelengths, but in most cases, its true identity remained a mystery. Some of them matched known galaxies, but others appeared to correspond to no obvious visible object at all. It was as though the sky held invisible beacons, glaring in radio light yet invisible to the human eye. This was the scene into which the story of 3C 273 would emerge. Astronomers of the mid-20th century were in a state of both excitement and confusion. They knew the sky was full of strange radio sources, but they did not yet understand what they were. Some suspected exotic stars or unusual galactic phenomena, while others wondered if they might be entirely new classes of objects. Optical astronomy still held dominance, but radio astronomy was quickly proving that the cosmos was far richer and stranger than anyone had imagined. It's important to remember the cultural atmosphere of the time as well. The mid-20th century was an era of rapid scientific and technological progress. Nuclear physics, space exploration, and relativity were reshaping how humanity viewed both the smallest particles and the largest scales of the universe. The public imagination was captivated by talk of rockets, satellites, and even extraterrestrial life. Against this backdrop, the discovery of mysterious radio signals from the depths of space carried a certain thrill, even a whiff of science fiction. Astronomers themselves were divided between cautious skepticism and bold speculation. Could these sources represent entirely new phenomena? Could they even hint at civilizations beyond Earth? While the majority leaned toward natural explanations, the sense of mystery was undeniable. For a science that had long relied on steady, methodical observation of stars and galaxies, the sudden flood of radio sources represented an unexpected frontier. By the time 3C273 was catalogued in the late 1950s, radio astronomy had become an established and rapidly expanding field. Large dishes like the one at Jodrell Bank in England and later the giant Arecibo Observatory in Puerto Rico opened new windows into the cosmos. The hunt was on to identify the nature of these strange radio beacons. Yet nobody anticipated just how revolutionary one of them would be. In fact, when the first true quasar was identified, it would force astronomers to rethink not only what objects existed in the universe, but the very scale of the cosmos itself. The stage was set for one of the most profound paradigm shifts in modern astronomy, and it began with the flicker of an enigmatic radio source in the constellation Virgo. When astronomers first began trying to make sense of these strange radio sources, they faced a profound problem of language. How do you describe something that doesn't fit into any of the known categories of celestial objects? Stars had long been familiar. Galaxies were by then accepted as immense collections of stars, and nebulae were clouds of dust and gas. But the new radio sources often defied classification. Some corresponded to distant galaxies or supernova remnants, but others were simply baffling. They didn't look like galaxies, they didn't behave like stars, and yet in photographs, they appeared as single points of light, indistinguishable from ordinary stars. This apparent contradiction led to the coining of a new term, quasar. The word itself is a contraction of quasi-stellar radio source. It captured the essence of the puzzle. These objects looked star-like, tiny, bright pinpoints when viewed through optical telescopes, but unlike ordinary stars, they were blasting out intense radio emissions. The phrase quasi-stellar meant star-like but not actually a star. That distinction was crucial, because while they resembled stars in appearance, their behavior suggested something much more exotic. The name was chosen in the early 1960s, around the time astronomers were making the first definitive identifications of these objects. Before quasar became common, they were often referred to in a more cumbersome way, as quasi-stellar radio sources. This was the language of the scientific papers of the day, a cautious, descriptive approach that simply pointed to the fact that these things looked like stars but were radio loud. Over time, as the community accepted them as a distinct class of objects, the shorter and catchier quasar took hold. It was elegant, easy to say, and hinted at their mysterious nature. It's worth pausing to consider how much of scientific history rests on the names we give to things. Quasar was not just a label, it shaped how astronomers thought about these objects. By emphasizing their quasi-stellar appearance, the term kept the paradox front and center. Here were star-like points of light that radiated like galaxies. They were both familiar and alien, a contradiction wrapped into a single word. The radio component of the name was equally significant, because at first, it was their radio emissions that made them stand out. Without radio astronomy, these bright pinpoints would have blended in with the countless stars in the sky, and nobody would have paid them much attention. But the name also carried a subtle bias. By highlighting their radio character, it suggested that all such objects would be strong radio emitters. In fact, astronomers would later discover that some quasars shine brilliantly in visible light but are faint in radio wavelengths. These came to be called radio-quiet quasars, a reminder that naming conventions often evolve as discoveries unfold. Still, the original term endured, and today quasar is used broadly to describe the entire class of extremely luminous, active galactic nuclei powered by supermassive black holes, whether they are strong or weak in radio emission. At the time of its coinage, though, the word quasar was revolutionary. It marked the recognition of a new phenomenon that didn't fit comfortably into existing categories. For a community of scientists trained to classify stars by spectral type and galaxies by shape, here was something that stubbornly refused to belong. It was like finding a creature in the wild that looked like a bird but roared like a lion. The name quasar became shorthand for the mystery itself, encapsulating both the appearance and the strangeness of these cosmic enigmas. And perhaps most importantly, the adoption of the term symbolized a cultural shift in astronomy. The mid-20th century was an era when the universe was becoming larger, stranger, and more dynamic with every discovery. The leap from stars to galaxies had already expanded humanity's perspective, and now quasars threatened to stretch it even further. To name them was to acknowledge them as something fundamentally new, a frontier waiting to be explored. In those early years, few could have predicted just how significant quasars would become. They were not simply curiosities or oddities of classification. They were windows into the distant past, laboratories of extreme physics, and markers of the universe's vast scale. Yet all of that meaning was still in the future. In the early 1960s, what astronomers had in their hands were star-like points of radio light, christened with a new name that carried both humility and wonder: quasars, the quasi-stellar radio sources. Among all the strange and puzzling radio sources catalogued in the early days of radio astronomy, one would ultimately stand out as the watershed moment in the story: 3C273. This was not just another entry in the Cambridge survey. It was the first quasar to be positively identified, the object that transformed the term quasi-stellar radio source from a curious label into a profound scientific category. In many ways, 3C273 can be seen as the Rosetta Stone of quasars, the key that unlocked an entirely new understanding of the universe. 3C273 lies in the constellation Virgo, one of the zodiac constellations visible in the night sky. Virgo itself is a rich region for astronomers, home to the Virgo cluster of galaxies and numerous bright stars. But within this constellation, tucked away in what appears to be an unremarkable star-like point of light, is one of the most important astronomical objects ever discovered. For an observer with an ordinary telescope, 3C273 doesn't look especially dramatic. It shines at about 12th or 13th magnitude in visible light, which means it is faint to the naked eye but accessible to amateur astronomers with a decent telescope. Its appearance is deceptively simple, a tiny speck of light, no different from the thousands of faint stars that pepper the background sky. And yet, beneath that ordinary disguise lies a cosmic engine of staggering power. What set 3C273 apart, at least initially, was not its visible appearance but its status in the third Cambridge catalogue of radio sources. In that catalogue, published in 1959, it was listed simply as one of many bright radio emitters scattered across the sky. There was no hint in the catalogue itself that this object would be any more significant than the others. The name 3C273 itself is not glamorous. It is simply the designation of the 273rd entry in that particular catalogue. But behind that dry label was a mystery waiting to be solved. When astronomers first turned optical telescopes to the position of 3C273, they were puzzled. Unlike some radio sources that could be traced to extended galaxies or nebulous patches of light, 3C273 looked like a star. There was no obvious galaxy surrounding it, no diffuse glow, nothing to indicate that it was anything other than an ordinary point of starlight. And yet, the radio data insisted otherwise. This object was blasting out radio waves at levels that no ordinary star could produce. Something didn't add up. The fact that 3C273 was located in Virgo only added to the intrigue. Virgo is already home to one of the nearest and richest clusters of galaxies, and astronomers were keenly aware that many mysteries lurked in that region. The discovery of a strange radio-loud, star-like object in this constellation raised immediate questions. Was it connected to the galaxies of the Virgo cluster? Was it a star within our own Milky Way that somehow behaved unlike any other? Or was it something altogether different, something beyond the categories astronomers were used to working with? Over time, 3C273 would become iconic because it was the first quasar to reveal its true nature to astronomers. Unlike other puzzling radio sources that remained stubbornly difficult to interpret, 3C273's optical counterpart was bright enough to be studied in detail with the best telescopes of the day. That brightness turned out to be a blessing, because it allowed astronomers to obtain a high-quality spectrum of its light. In the early 1960s, this was still a challenging task, but without such data, the mystery would have remained unsolved. 3C273, by virtue of being unusually luminous compared to other candidates, provided the perfect laboratory to unlock the secret of quasars. Even before its spectrum was understood, 3C273 began to attract attention because of subtle features in its appearance. Careful observations revealed that it wasn't just a point of light. Faintly extending from it was a tiny jet-like structure. This was no ordinary star. Stars, no matter how peculiar, do not produce narrow, collimated jets of material extending into space. That faint feature hinted that 3C273 was fundamentally different, and that its true identity lay far beyond the boundaries of stellar physics. Today, when astronomers or enthusiasts talk about quasars, 3C273 almost always comes up first. It holds a special place in the history of science because it was the first. Before its identification, quasars were nameless enigmas, sources of radio noise without clear explanation. After 3C273, the pieces began to fall into place. It would be the breakthrough object that forced astronomers to confront the reality of supermassive black holes, accretion disks, and an active universe far more violent and energetic than anyone had dared to imagine. And so, though it may look to the eye like an inconspicuous star in Virgo, 3C273 is a milestone in humanity's exploration of the cosmos. It is the quasar that revealed itself first, the one that opened the door. It is to introduce the beginning of an era in which astronomy had to expand its horizons beyond galaxies, beyond stars, to embrace forces and energies that stretched imagination to its limits. The story of 3C273 begins not with a telescope aimed at the night sky, but with radio antennas scanning invisible wavelengths. In the mid-20th century, the University of Cambridge became one of the centers of this emerging field of radio astronomy. Scientists there, led by figures like Martin Ryle and his colleagues, were pioneering new techniques for detecting and cataloging radio emissions from space. Their efforts culminated in a series of surveys that systematically charted the radio universe. The first two Cambridge catalogues had already listed hundreds of sources, but the third Cambridge Catalogue of Radio Sources, or simply 3C, published in 1959, was a leap forward in scale and precision. The 3C catalogue contained nearly 500 radio sources, each one a beacon of electromagnetic energy detected far beyond the visible spectrum. To construct this catalogue, astronomers used radio interferometry, combining signals from multiple antennas to sharpen their ability to pinpoint where the signals were coming from. This was a challenging task at the time, since early radio telescopes did not have the pinpoint accuracy of optical ones. As a result, the positions of radio sources in the sky were often given with only rough accuracy, sometimes off by several arc-minutes or more. Still, the catalogue was an extraordinary achievement. For the first time, astronomers had a systematic list of mysterious objects that glowed in radio wavelengths, many with no obvious counterparts in visible light. Among the hundreds of entries in the catalogue was one that seemed unremarkable at first glance: 3C273, the 273rd object listed. At the time, it was simply another bright radio emitter, plotted among the many others that populated the survey. Nothing about its initial listing suggested that it would later become one of the most important astronomical discoveries of the century. To the researchers compiling the catalogue, 3C273 was just a strong radio source in the constellation Virgo, and on their map of the radio sky. The way these sources were catalogued highlights the scientific climate of the time. The 3C list was not about solving mysteries but about creating the foundation for future work. By identifying, numbering, and describing radio emitters, astronomers were essentially creating a roadmap for follow-up observations. Some of these objects would turn out to be galaxies known from optical surveys, others supernova remnants, and still others remained unexplained. At first, 3C273 was lumped into that last category, an unexplained, but very real, beacon of radio waves. The entry of 3C273 in the catalogue contained its approximate coordinates and a measure of its brightness in radio wavelengths. That was all. It didn't carry with it any assumptions about what kind of object it might be. Yet its brightness made it a tempting target for follow-up studies. Stronger sources were easier to locate more precisely, and they offered better chances of identifying a visible counterpart. For astronomers eager to connect the dots between the radio and optical skies, 3C273 was a natural candidate. But there was a fundamental difficulty. At that time, aligning radio sources with optical objects was like trying to match two different maps of the same territory, one blurry and the other sharp. Optical telescopes could pinpoint stars and galaxies with extreme accuracy, but radio telescopes, especially in the 1950s, had fuzzier resolution. When you looked for the optical counterpart of a radio source, you often had to search a relatively large patch of sky, which might contain dozens of stars or galaxies. Identifying the true source among them was like hunting for a needle in a haystack. For many 3C sources, this task proved impossible. 3C273, however, was different. Because of its relative brightness in radio, astronomers could refine its position better than for most other sources. Over the following years, attempts were made to narrow down its optical counterpart. Still, even with that advantage, the identification process was not straightforward. The fact that 3C273 looked like an ordinary star made it even trickier. Nobody expected that such a star-like speck could be the source of the tremendous radio signal catalogued by the Cambridge Group. To most astronomers of the era, stars were not radio loud. A star emitting at such intensities was inconceivable. This dissonance, the catalogue telling them that a strong radio source was present, while the optical telescopes showed only what looked like a normal faint star, created both frustration and intrigue. Was the catalogue wrong? Was there an invisible object hiding near that star? Or was it possible that this pinprick of light really was the source of the radio emission? Such questions lingered for years as 3C273 sat quietly in the catalogue, awaiting the deeper scrutiny that would finally reveal its true nature. At the time of its listing, though, there was no sense of impending revolution. For the astronomers who compiled the 3C catalogue, 3C273 was one data point among hundreds, its significance hidden, waiting for someone to look closer. The fact that such a monumental breakthrough could hide under so ordinary a name is part of what makes the story so remarkable. It reminds us that often in science, great discoveries begin as routine entries in a list, anonymous numbers on a page, their importance revealed only when curiosity and persistence bring them into sharper focus. Once 3C273 had been marked down as a strong radio source in the third Cambridge catalogue, the real challenge began, matching that invisible radio beacon to a visible object in the sky. This was a process that tested not only the technology of the time but also the very assumptions astronomers carried about what could and could not produce such intense emissions. The early years of radio astronomy were filled with a frustrating gap between detection and identification. Radio telescopes could pick up powerful signals, but their resolution was coarse compared to optical instruments. Imagine trying to locate a single candle flickering in a distant city using binoculars smeared with fog. That was roughly the level of precision astronomers were working with. The coordinates given in the 3C catalogue were good enough to point in the right direction, but within the error margin, there could be many candidate stars or galaxies. Which one was the real source? With 3C273, the mystery deepened when optical telescopes turned toward its location. What they saw, or thought they saw, was completely ordinary. There was a faint, star-like point of light in Virgo, seemingly indistinguishable from thousands of background stars scattered across the night sky. Nothing about its appearance hinted at the violent energies suggested by its radio signal. It looked small, quiet, unremarkable. To most astronomers, that was the end of the trail. Stars simply didn't generate such powerful radio emissions, so surely this faint speck couldn't be the culprit. Something else had to be there, some hidden galaxy or faint nebulosity just out of sight. Part of the challenge was psychological as much as technical. Astronomers were trained to think of stars as individual, nuclear-powered furnaces, objects like our Sun but at varying distances. Radio astronomy was new, and there was no precedent for stars being radio bright to this degree. Galaxies, on the other hand, were beginning to emerge as plausible candidates, since some galaxies, like Cygnus A, were already known to produce enormous radio emissions. But a galaxy looks extended through a telescope. It doesn't masquerade as a pinpoint. That left 3C273 as a puzzle that didn't fit either box. Too star-like to be a galaxy, too radio-loud to be a star. To complicate matters further, the exact position of 3C273's radio emissions was not perfectly pinned down at first. The uncertainties meant that astronomers had to be cautious in declaring any single optical object the counterpart. This was an era before sophisticated digital imaging or computerized cross-matching. Instead, astronomers compared photographic plates of the sky with radio maps that looked, by modern standards, extremely crude. A small error in alignment could mean weeks or months of chasing the wrong star. Despite these obstacles, astronomers persisted. The unusual brightness of 3C273 in both radio and optical made it an enticing target. If they could pin down its optical counterpart with certainty, it would provide a crucial step toward understanding the nature of these strange quasi-stellar objects. Observers began to look more carefully at that faint star-like point in Virgo. Some noted subtle features in photographic plates, a faint smudge, a hint of extension, something not quite stellar. But the evidence was ambiguous, and many still doubted that this tiny speck could possibly be the true radio source. One of the strategies that helped was to observe occultations, moments when the moon passed in front of a radio source. By timing the exact moment when the radio signal disappeared behind the lunar limb, astronomers could dramatically improve their positional accuracy. This technique was crucial for narrowing down the candidate list for 3C273. In a sense, the moon became an accidental measuring tool, drawing a sharp line across the radio sky and allowing astronomers to triangulate the source with far greater precision. Even with these refinements, the optical identification remained controversial. The faint point of light was simply too unassuming. It looked like a star, it behaved like a star in terms of its appearance, and yet it could not be a star if the radio data were to be believed. For years, this contradiction simmered without resolution. Astronomers had in front of them an object that defied expectations but lacked the clear markers that could place it in a familiar category. It is hard, looking back now, to appreciate just how radical the idea of a star-like object producing such immense energy seemed at the time. Today, with the concept of quasars well established, the match between the radio source and the optical point seems obvious. But in the early 1960s, this was a puzzle that stretched astronomers' imaginations to the breaking point. The visible counterpart was there, staring them in the face, but it was so counterintuitive that many simply couldn't accept it as the answer. This period of uncertainty was critical, though, because it forced astronomers to refine their methods and question their assumptions. It showed that the universe was capable of presenting objects that looked familiar but were, in reality, profoundly alien. And it set the stage for the breakthrough that would come in 1963, when the true nature of 3C273 was finally revealed in spectacular fashion. By the early 1960s, 3C273 had become an object of intense curiosity. Radio astronomers had identified its position with increasing accuracy, optical astronomers had noted its deceptively star-like appearance, and yet no one had managed to explain what it truly was. The breakthrough came in 1963, thanks to the work of Martin Schmidt, a Dutch-born astronomer working at Caltech in Pasadena, California. What Schmidt achieved was nothing short of revolutionary. He looked at the light of 3C273 more carefully than anyone had before, and in doing so, he cracked open the mystery of quasars. The key tool Schmidt used was spectroscopy. In astronomy, a spectrum is the fingerprint of light. By splitting starlight into its component wavelengths, astronomers can identify which elements are present, how hot the object is, and how it's moving relative to Earth. For decades, spectra had been the foundation of stellar classification. Every star's light bore distinctive absorption or emission lines, marking the presence of hydrogen, helium, calcium, and other familiar elements. If 3C273 was indeed just an unusual star, its spectrum should reveal that fact. Schmidt obtained a high-quality spectrum of 3C273 using the 200-inch Hale telescope at Palomar Observatory, at the time, the most powerful telescope in the world. What he saw, however, was deeply puzzling. Instead of the tidy, familiar pattern of lines expected from a star, the spectrum of 3C273 showed a series of strong emission lines that simply did not match any known atomic signatures at normal wavelengths. For weeks, Schmidt struggled with the data, trying to reconcile the strange spectrum with existing categories of objects. Was it some rare type of star? Was it an exotic nebula? The lines seemed to defy classification. The turning point came when Schmidt realized that the lines might not be unrecognizable at all, they might just be shifted. In particular, the hydrogen-Balmer series, one of the most common and well-understood sets of spectral lines in astronomy, seemed to be present, but at wavelengths far longer than expected. It was as if the entire fingerprint of hydrogen had been stretched. Schmidt quickly understood what this meant. The light was redshifted. Redshift occurs when light from an object moving away from us is stretched to longer, redder wavelengths by the expansion of the universe. Astronomers had known about redshift since Edwin Hubble's discovery in the 1920s that galaxies are receding from us, with more distant galaxies receding faster. But the amount of redshift in 3C273 spectrum was staggering. Schmidt calculated that its redshift corresponded to a velocity of about 47,000 km per second, and more importantly, a distance of nearly 2 billion light-years. This was an order of magnitude beyond anything anyone had expected for an object that looked like a star. In that moment, the pieces fell into place. The strange, unclassifiable emission lines weren't exotic at all. They were ordinary hydrogen, but redshifted to such an extent that they seemed alien. What Schmidt had discovered was not a nearby star, but a luminous beacon shining from billions of light-years away. This faint, star-like object was in fact unimaginably distant, and its brilliance must therefore be extraordinary. When Schmidt announced his findings in early 1963, the astronomical community was stunned. The implications were immediate and profound. If 3C273 was truly that far away, then it had to be radiating as much energy as an entire galaxy, or more, all from a region so compact that it looked like a star. This was not just a new kind of object, it was a new category of cosmic phenomenon. Quasars had arrived, and astronomy would never be the same again. It's difficult to overstate the drama of this moment. For years, astronomers had wrestled with radio sources that defied explanation. Many of them suspected that the solutions lay in exotic stellar remnants or unusual galactic phenomena. Few were prepared to accept that a star-like point of light could be billions of light-years away and yet still shine so brightly. Schmidt's identification of 3C273's redshift shattered those preconceptions. It revealed that the universe was capable of producing compact objects of staggering luminosity, powered by processes beyond the reach of ordinary stellar physics. The historic discovery didn't just answer questions about one radio source, it opened up an entirely new field. Suddenly, dozens of other quasi-stellar objects with strange spectra could be reinterpreted in the same way. They weren't nearby oddities, they were distant, powerful engines. Within months, quasars became the hottest topic in astronomy, and Schmidt's work became a landmark in the history of science. 3C273 thus moved from being an anonymous entry in a radio catalogue to being the first identified quasar, the prototype of a new class of cosmic powerhouses. Schmidt's brilliance lay not in discovering something entirely new, but in recognizing the familiar hidden within the strange. By daring to consider that the odd spectral lines were just ordinary hydrogen shifted to the extreme, he revealed the true scale of the universe in a way no one had before. The breakthrough with 3C273 hinged on one of the most important concepts in modern astronomy, redshift. To fully appreciate just how shocking Martin Schmidt's realization was, we need to step back and understand what redshift actually means. Light, like sound, comes in waves. When a fire truck approaches with its siren blaring, the pitch sounds higher as the waves are compressed, and when it passes and moves away, the pitch drops as the waves are stretched out. This is known as the Doppler effect. Light behaves in much the same way. If a luminous object in space is moving toward us, its light waves are compressed, shifting toward the bluer end of the spectrum. If it is moving away, the light waves are stretched, shifting toward the redder end. That stretching is what we call redshift. In the 1920s, Edwin Hubble demonstrated that distant galaxies almost all show redshifted spectra. Not only that, but the farther away a galaxy is, the greater the redshift of its light. This discovery led to the conclusion that the universe is expanding, and that redshift can be used as a kind of cosmic ruler. The higher the redshift, the farther away the object lies. By the mid-20th century, this was a well-accepted principle, and astronomers routinely measured redshifts of galaxies to determine their distances. But quasars presented something altogether stranger. When Schmidt examined the spectrum of 3C273 in 1963, he initially found the emission lines baffling. They didn't match the usual fingerprints of elements seen in stars or galaxies. Yet the spectrum had strong, sharp lines, which meant they had to correspond to something known. The aha moment came when Schmidt considered that the hydrogen-Balmer lines, patterns so familiar they were second nature to astronomers, were present, but not where they should have been. Instead of appearing at their normal wavelengths in the blue and violet part of the spectrum, they were displaced far toward the red. Schmidt realized that if he interpreted these strange lines as hydrogen that had been redshifted, they suddenly made perfect sense. The lines matched hydrogen exactly, but only if they were shifted by about 15% toward longer wavelengths. That corresponded to a redshift of Z equals 0.158, meaning the light was stretched by 15.8% compared to its original wavelength. To put that in perspective, most galaxies known at the time had redshifts far smaller than this. A redshift of 0.158 placed 3C273 at nearly 2 billion light-years away, an almost unthinkable distance for what looked like a single, faint star. This was the revelation. The mystery wasn't that the spectral lines were exotic or unknown, but that they were ordinary hydrogen lines seen through the lens of an expanding universe. Schmidt had essentially recognized that the cosmos was playing a trick on human perception. What looked nearby was, in fact, staggeringly distant. The implications hit like a thunderclap. If 3C273 was billions of light-years away and still visible through telescopes as a bright point of light, then it had to be radiating an extraordinary amount of energy, outshining entire galaxies, yet concentrated in a region so small that it looked star-like. No known mechanism in astrophysics at the time could explain this. Stars could not do it. Ordinary galaxies could not do it. This was something new, a kind of object that had never been theorized in textbooks. Astronomers who heard Schmidt's announcement at first reacted with disbelief. Could the interpretation be wrong? Perhaps the redshift was not due to distance but to some unknown effect within the object itself? Such objections arose because the idea that a star-like point of light could be billions of light-years away seemed outrageous. But the logic of the spectrum was airtight. The lines matched hydrogen perfectly once redshift was accounted for, and hydrogen is the most abundant element in the universe. What Schmidt had uncovered in 3C273 was the first clear demonstration that quasars were not just nearby curiosities but cosmologically distant powerhouses. The redshift revelation transformed them from puzzling radio dots into probes of the farthest reaches of the universe. It also extended Hubble's law of redshifted galaxies into a new and extreme regime, proving that the same cosmic expansion that governs galaxies also applied to these strange, star-like objects. The discovery was so paradigm-shattering because it forced astronomers to admit that the universe could produce energies far beyond anything they had considered possible. A star burning hydrogen in its core was no longer the ultimate engine of cosmic light. Quasars, with their redshifted hydrogen lines, showed that black holes, accretion disks, and relativistic jets were waiting to be discovered as the true engines of the cosmos. So when Schmidt recognized that the odd spectrum of 3C273 was just hydrogen stretched by the expansion of space, it wasn't just a clever piece of detective work. It was the moment when the scale of the universe expanded dramatically in human understanding. That simple pattern of lines, shifted far beyond expectations, became the gateway to an entirely new vision of cosmic power. When Martin Schmidt announced that 3C273's spectral lines were simply hydrogen redshifted far beyond what anyone had expected, the scientific world was caught off guard. The implications of that redshift were staggering. A redshift of 0.158 placed 3C273 at roughly 2 billion light-years away. For perspective, the light that reached Schmidt's telescope had left the quasar when life on Earth was still in its earliest stages of evolution, before the first multicellular organisms had even appeared in the oceans. This meant that by observing 3C273, astronomers were looking back in time across a vast swath of cosmic history. But it wasn't just the distance itself that shocked astronomers, it was what that distance implied about the quasar's brightness. To be visible at all across 2 billion light-years, 3C273 had to be unleashing an unimaginable torrent of energy. Ordinary stars, even the brightest supergiants, fade into invisibility long before such distances. Galaxies filled with billions of stars can still be seen at those ranges, but 3C273 didn't look like a galaxy, it looked like a single star. How could a point-like object rival, or even surpass, the luminosity of entire galaxies? This realization created a sense of unease in the astronomical community. For decades, the hierarchy of cosmic objects had been clear. Stars powered by nuclear fusion were the fundamental engines of light and energy. Galaxies were the grand assemblies of stars, and nebulae were clouds of gas and dust. Now here was something that defied that neat order. A quasar like 3C273 looked like a star but behaved like something far beyond the scale of galaxies. The shock was compounded by the fact that, until then, astronomers had assumed that star-like objects were nearby by default. The very word star implies proximity within our galaxy. A point of light that looked like a star but was actually billions of light-years away overturned that assumption. It meant the universe could disguise its most powerful objects in the humblest forms, tricking the human eye into seeing something ordinary when, in truth, it was extraordinary. Some astronomers resisted the conclusion at first. The idea that an object could be so distant and yet so bright seemed absurd. Alternative explanations were floated. Perhaps the redshift wasn't caused by cosmic expansion but by some unknown physical process inside the object itself. Maybe quasars were relatively nearby but somehow mimicked high redshifts through exotic physics. These ideas gained some traction because they felt safer than accepting that a star-like dot could outshine an entire galaxy. Yet, the more data came in, the harder it became to deny the reality. Other quasi-stellar radio sources began to yield similar spectra, with redshifts even higher than 3C273's. If 3C273 had seemed shocking at 2 billion light-years, some quasars were now being placed at 10 billion light-years or more. The universe was telling astronomers something unmistakable. It was filled with extraordinarily powerful objects scattered across immense distances, and they had only just begun to recognize them. The distance shock wasn't just about the numbers on paper, it was about a shift in worldview. Before 3C273, astronomers thought of the universe as vast but still somewhat tame. Galaxies drifted apart, stars lived and died, nebulae glowed faintly. After 3C273, the universe was revealed to be violent, dynamic, and filled with engines of power that dwarfed anything humans had previously imagined. The quasar discovery forced a reconsideration of cosmic scale, not only in terms of space but also in terms of energy. To give a sense of how dramatic this was, if you could somehow bring 3C273 as close to Earth as one of the bright stars in our night sky, it would shine so intensely that it would outblaze the sun and bathe the Earth in lethal radiation. Yet, across billions of light-years, it still managed to appear bright enough to be studied in detail. That fact alone was enough to leave astronomers reeling. The shock of 3C273's distance was not just a fleeting moment. It lingered, reshaping research priorities for decades. Suddenly, quasars were at the forefront of astronomy. The question was no longer what are they, but how can anything in the universe produce such staggering amounts of energy? In the years that followed, that question would lead directly to the idea of supermassive black holes and accretion disks as engines of cosmic power. But in 1963, all of that lay ahead. For the moment, the astronomical community was grappling with the enormity of what Schmidt had revealed. A star-like point of light in Virgo was, in fact, one of the most distant and most luminous objects in the universe. The discovery that 3C273 was billions of light-years away left astronomers reeling. But the true astonishment came when they tried to reconcile its distance with its brightness. This became known as the brightness paradox. If the redshift was real, and all evidence pointed to it being real, then the light we were seeing from this quasar had traveled across 2 billion years of expanding space, surviving unimaginable stretches of cosmic time. And yet, when that light arrived at Earth, it wasn't faint and barely detectable. It was bright, shockingly bright. In fact, 3C273 is so luminous that even through a modest backyard telescope, it can be seen as a star-like point of light. It is, to this day, one of the very few quasars visible to amateur astronomers with relatively small instruments. This simple fact astonished professionals in the 1960s. They were used to faint smudges of distant galaxies requiring hours of photographic exposure to record. But here was an object billions of light-years away shining clearly enough to stand out in the eyepiece. The paradox lay in scale. To appear that bright from so far away, 3C273 had to be radiating energy equivalent to hundreds of billions of suns, comparable to the output of an entire massive galaxy. And yet, unlike a galaxy, which sprawls across tens of thousands of light-years, 3C273 appeared point-like, as if all that luminosity were coming from a region no larger than a solar system. The sheer intensity of energy defied any explanation known at the time. It was as if a single match, seen from across the width of a continent, shone as brightly as a stadium floodlight. That was the level of contradiction astronomers were forced to confront. How could something so small behave as though it were an entire galaxy's worth of light squeezed into a pinpoint? This paradox was not just a curiosity. It was a direct challenge to astrophysics itself. Stars release energy through nuclear fusion, galaxies shine because of the combined light of billions of stars, and nebulae glow by reflecting or reprocessing starlight. None of these mechanisms could account for what was happening in 3C273. Whatever the source of its power was, it had to be something entirely different, something capable of converting matter into energy with an efficiency far beyond the nuclear reactions in stars. For astronomers in the early 1960s, this was almost heretical. The universe had always been seen as operating within a fairly well-understood set of processes. Yet here was proof that there was a whole new class of phenomena waiting to be explained. At first, the paradox sparked speculation. Could quasars be powered by swarms of supernovae going off all at once? Could they be massive collections of neutron stars radiating in unison? Ideas piled up, but none fit the observations. The variability of quasars, the fact that their brightness flickered over short timescales, implied that their emitting regions were compact, far too compact for something on the scale of a whole galaxy. This was one of the most disorienting aspects of the brightness paradox. On one hand, quasars had to be as luminous as galaxies. On the other hand, their star-like appearance and variability suggested their energy came from a region not much larger than our solar system. Somehow, the cosmos was producing objects that combined galaxy-scale luminosity with star-scale compactness. It was a contradiction that would eventually lead astronomers to the idea of supermassive black holes feeding on accretion disks, but in 1963 that explanation was still years away. The paradox also forced astronomers to rethink how they measured brightness. They had long relied on apparent magnitude, a scale based on how bright an object looks from Earth. But apparent brightness can be misleading because it doesn't account for distance. With quasars, apparent brightness had to be combined with redshift measurements to determine absolute luminosity, the true, intrinsic energy output of the object. Doing so revealed just how absurdly powerful 3C273 was. In terms of raw luminosity, it outshone not just typical galaxies but even the most active starburst galaxies known. And yet, when astronomers pointed their telescopes at it, 3C273 gave them no majestic spiral arms, no glowing nebula clouds, no stellar clusters, only a featureless, star-like speck. The irony was striking. The most powerful object in the known universe appeared as ordinary as a star you could pick out of any constellation. This contradiction gave quasars their name, quasi-stellar radio sources, because in appearance they mimicked stars, while in reality they were something vastly more powerful and distant. The brightness paradox of 3C273 became one of the central mysteries of 20th century astronomy. It forced a paradigm shift. No longer could astronomers assume that point-like sources were nearby stars. Some of them were, in fact, beacons shining from the edges of the observable universe. And no longer could they assume that nuclear fusion in stars represented the peak of cosmic energy production. Something far more exotic was at work, something that would eventually be tied to the monstrous engines of gravity at the hearts of galaxies. When astronomers and even amateur stargazers turn their telescopes toward 3C273, the experience can be strangely underwhelming at first glance. Despite being one of the most luminous and energetic objects in the known universe, it doesn't present the kind of grand spectacle you might expect. Through a telescope, even a large one, 3C273 does not sprawl across the eyepiece like a galaxy or blaze with the colorful tendrils of a nebula. Instead, it appears deceptively simple, a pinpoint of light, indistinguishable at first sight from an ordinary star. This star-like appearance is precisely why quasars were so puzzling to astronomers in the early days of their discovery. 3C273's light is compacted into such a small angular size that it cannot be resolved into any structure by ground-based telescopes without advanced imaging techniques. To the naked eye through an instrument, it looks almost disappointingly mundane. But that faint, star-like spark holds a story that stretches across billions of years and outshines galaxies. Yet, with closer inspection and under the right conditions, 3C273 reveals one of its most striking features: a faint jet of light extending outward. This jet is not immediately obvious to all observers. For most amateurs using small telescopes, the quasar will remain a bright point of light and nothing more. But for those with access to larger instruments, especially those with dark skies and careful observation techniques, the faint wisp of its jet can be glimpsed. It extends a few arcseconds from the central point, angled slightly away from the bright core, like a ghostly thread unraveling from the star-like beacon. This jet was one of the earliest clues that 3C273 was not simply a star. Stars don't project visible streams of light or matter across space. The presence of a jet suggested violent processes at work. Jets are typically associated with compact, energetic regions like pulsars or active galactic nuclei. In the case of 3C-273, the jet is composed of particles accelerated to nearly the speed of light, moving outward along the poles of the central engine. That jet shines because it emits radiation across many parts of the spectrum, from radio waves to visible light. For professional astronomers, the jet of 3C-273 became an invaluable tool for understanding the physics of quasars. Photographs taken with long exposures revealed it clearly, a narrow, linear structure stretching outward from the core, almost like a miniature lighthouse beam projected into the void. Today, images from the Hubble Space Telescope show the jet in exquisite detail, revealing knots and twists that correspond to shockwaves and magnetic interactions. But even before Hubble, ground-based observatories had already captured its presence, lending credibility to the idea that quasars were powered by processes far more extreme than anything happening in stars. To the average skywatcher, though, 3C-273 remains a curious paradox. On a good night, with a telescope of modest aperture, one can point toward the constellation Virgo and, with a bit of patience, spot the faint dot of light that is this legendary quasar. Knowing what it represents, the first quasar ever identified, an object 2 billion light-years away that blazes brighter than galaxies, transforms that tiny speck into something awe-inspiring. It's worth noting that 3C-273 is unique among quasars in this regard. Most quasars are far too faint to be seen with amateur equipment, hidden deep in the night sky as tiny flickers detectable only by powerful observatories. But 3C-273 is different. It is the brightest quasar visible from Earth, and for that reason, it has earned a special place in both professional astronomy and the world of amateur stargazing. For many enthusiasts, seeing 3C-273 in the eyepiece is like reaching across the universe, a reminder that the light striking their eye set out when the Earth was still young, carrying with it the story of cosmic violence and unimaginable energy. The appearance of 3C-273 in telescopes is thus both deceptive and profound. Deceptive, because it looks like a simple star. Profound, because hidden in that simplicity is the signature of one of the most extraordinary discoveries in the history of astronomy. And with its faint but persistent jet, it offers a rare visual clue to the tremendous forces at work in its heart. The jet of 3C-273 is one of its most iconic features, and it remains a cornerstone in our understanding of quasars. While the object itself shines as a star-like point in telescopes, the jet is the feature that truly sets it apart, turning what appears to be just another in the sky into a cosmic laboratory for extreme physics. Jets are not something you associate with stars. Stars radiate light in all directions. But quasars, driven by processes at the very edge of physics, can launch colossal streams of matter and energy outward in narrow beams. 3C-273 was one of the first objects where this phenomenon was actually seen. This jet is a beam of plasma accelerated to nearly the speed of light, extending tens of thousands of light-years from the quasar's core. Imagine the scale: Earth, the Sun, and the entire solar system would be less than a speck compared to the length of this outflow. Even the Milky Way, our galaxy, would be dwarfed if you placed such a jet alongside it. The fact that such a structure can emerge from what looks like a star-like point of light boggles the mind. What makes 3C-273 so remarkable is that its jet is visible not only to massive observatories but, under the right conditions, even to skilled amateur astronomers using powerful backyard telescopes. With a telescope of 10 to 12 inches or larger, under dark skies, the jet can be glimpsed as a faint streak protruding from the pinpoint of the quasar itself. To see something ejected by an object 2 billion light-years away is, in itself, an act of connecting directly with the deepest forces in the universe. It's a rare opportunity for amateurs to observe relativistic astrophysics in action with their own eyes. When astronomers study the jet in greater detail with instruments like the Hubble Space Telescope and the Chandra X-ray Observatory, they find a structure filled with knots, twists, and shocks. These are not random. They are the signatures of particles being hurled out at relativistic speeds, close to the speed of light, interacting with magnetic fields and interstellar material. The jet glows across the spectrum. In radio waves, it appears as a long, continuous structure. In visible light, it becomes a faint streak. In X-rays, it reveals intense hotspots where particles are being accelerated to extreme energies. One of the most fascinating aspects of jets like the one from 3C273 is the role of relativity. Because the material inside the jet is moving so close to the speed of light, strange effects predicted by Einstein's theory of relativity become visible. For example, portions of the jet appear to move faster than light itself, a phenomenon called superluminal motion. Of course, nothing can exceed the speed of light, but the geometry and timing of light signals emitted by objects moving at relativistic speeds can create the illusion of superluminal travel when observed from Earth. 3C273 was one of the first sources where this effect was observed, further cementing its importance as a case study in high-energy astrophysics. The jet also plays a crucial role in solving the brightness paradox of quasars. The sheer intensity of light coming from 3C273 is not only the result of its accretion disk but also enhanced by the beaming effect of relativistic jets. These jets can direct radiation in narrow cones, amplifying the apparent brightness when the beam happens to be oriented near our line of sight. In the case of 3C273, its orientation is favorable enough that Earth lies in view of its outflow, making it even more brilliant to us than it might otherwise appear. What's even more extraordinary is how these jets help transport energy across intergalactic space. The jet from 3C273 carries with it tremendous amounts of energy, injecting it into the surrounding intergalactic medium. This has profound consequences for the environment around quasars, influencing the formation of galaxies, heating the intergalactic gas, and shaping cosmic structures on scales far beyond the galaxy that hosts the quasar. In this sense, the jet is not just an astronomical curiosity, it's a fundamental mechanism in the cosmic ecosystem. For the public and amateur astronomers, though, there is something poetic about the jet of 3C273. To look through a telescope and see not just a point of light but a thin, faint streak extending away from it is to glimpse, in a very direct way, the raw power of a supermassive black hole at work. That faint streak is material that has been accelerated to near-light speed and launched across thousands of light-years. It's a signature of the universe at its most violent and creative, recorded as a subtle etching of light in the night sky. In the decades since its discovery, the jet of 3C273 has been imaged, analyzed, and modeled countless times. It has taught astronomers about magnetic fields, relativistic particle acceleration, and the connection between black holes and galaxy evolution. But beyond all the physics, its enduring allure lies in its visibility. An ordinary telescope, wielded by a dedicated skywatcher, can connect us to a phenomenon that speaks of energies and scales far beyond human imagination. When astronomers first confronted the mystery of quasars, they were faced with a staggering puzzle. How could something no larger in appearance than a star produce as much light as an entire galaxy? The answer, which slowly came into focus over the years following the discovery of 3C273, turned out to be both elegant and terrifying. Quasars are powered not by ordinary stars, not by clusters of stars, but by supermassive black holes, cosmic engines millions to billions of times more massive than our Sun, sitting at the hearts of galaxies and feeding on their surroundings. To understand why this was such a groundbreaking idea, consider what black holes represent. For a long time, they were little more than mathematical curiosities predicted by Einstein's general theory of relativity. They were regions of space where gravity was so intense that nothing, not even light, could escape. Most astronomers in the early 20th century doubted they existed in reality. But the paradox of quasars forced a reconsideration. No ordinary process of stellar fusion or galactic light production could explain their brightness. Only a mechanism capable of converting mass into energy with an efficiency far higher than fusion could do it. Nuclear fusion, the process that powers stars like our Sun, converts less than 1% of mass into energy. A black hole feeding on matter, however, can convert up to 40% of the mass of the infalling material into energy through gravitational processes before the matter crosses the event horizon. That's orders of magnitude more efficient than the core of any star. Suddenly, the unimaginable luminosity of 3C273 began to make sense. At the heart of 3C273 lies one of these monsters, a supermassive black hole weighing perhaps hundreds of millions of solar masses. Surrounding it is a whirling accretion disk of gas, dust, and perhaps even disrupted stars, all spiraling inward under the pull of its immense gravity. As the material accelerates and compresses, it heats to millions of degrees, radiating across the electromagnetic spectrum, from radio waves to visible light to X-rays and even gamma rays. What we see as the brilliant glow of the quasar is, in fact, the death scream of matter as it is torn apart and consumed by gravity. The black hole itself, paradoxically, remains invisible. Its event horizon swallows all light. What makes the quasar shine is the environment around it, the inflowing disk of matter, the magnetic fields twisting and snapping, the relativistic jets blasting outward along the poles. Quasars are not black holes sitting quietly in the dark. They are black holes in the act of feasting, radiating with a ferocity that can be seen across billions of light-years. The supermassive black hole explanation also resolved the riddle of the compact size of quasars. Variability studies showed that quasars could flicker in brightness over timescales of days or weeks. That implied their emitting regions were small. After all, light cannot vary faster than the time it takes to cross the emitting region. A whole galaxy cannot flicker on the scale of days. But a region the size of a solar system could. The idea of a black hole and its immediate environment fit this perfectly. As the black hole devours material, not all of it vanishes across the horizon. Some is caught in magnetic fields and funneled into the colossal jets, which we see streaming from 3C273. Others heat and radiate intensely, producing the characteristic emission lines and broad spectrum that distinguish quasars from ordinary stars or galaxies. What emerges is an energy conversion process unlike anything else in nature, gravity itself harnessed to power cosmic lighthouses. It is astonishing to think that what once baffled astronomers as a star-like enigma turned out to be the visible signature of one of the most extreme objects imaginable. Without the puzzle of 3C273, the recognition that galaxies harbor supermassive black holes at their centers might have taken decades longer. Today, we know that nearly every large galaxy has such a black hole at its core, though not all of them are active. Quasars are simply the black holes in their wild, voracious youth, when they were feeding rapidly and transforming matter into energy at phenomenal rates. The realization that supermassive black holes could power quasars was one of the most profound paradigm shifts in 20th century science. It connected the small scale of relativity with the vast scale of cosmology, showing how a single compact object could dominate the light output of a galaxy. And in 3C273, this concept found its first clear and dramatic proof, a beacon across time and space, lit by the hunger of a cosmic giant devouring its surroundings. When we speak of quasars being powered by supermassive black holes, it's important to remember that the black hole itself is not what we see. Black holes, by definition, allow no light to escape. The real spectacle comes from the swirling maelstrom of material that gathers around them, the accretion disk. This disk is not just a passive structure, it is the very heart of a quasar's brilliance, the place where matter is transformed into pure radiant energy before plunging into darkness. Imagine gas and dust drifting through a galaxy. Most of it remains diffuse, spread thinly between stars, but some of it strays too close to the black hole at the galaxy's center. Gravity seizes hold of it, drawing it inward. Rarely does this material fall straight in. Instead, it carries some degree of angular momentum. Essentially, it's orbiting as it falls. Like water swirling down a drain, the matter spirals inward, flattening into a disk as it does so. This is the accretion disk, a cosmic whirlpool feeding the hunger of the black hole. But this spiral is not a quiet journey. As the material in the disk moves closer to the event horizon, it accelerates to extraordinary speeds, approaching a significant fraction of the speed of light. The inner regions of the disk are like a racetrack where gas particles circle at nearly unimaginable velocities. This motion creates friction, not the everyday friction of rubbing surfaces but viscous interactions and turbulent magnetic stresses between different layers of orbiting gas. The result is intense heating, so intense that the accretion disk becomes one of the hottest and most luminous objects in the universe. In 3C273, the accretion disk radiates across the electromagnetic spectrum. The outer parts of the disk glow in ultraviolet and visible light, giving quasars their brightness in optical telescopes. Closer in, where the gas is hotter, the emission shifts into X-rays. Some regions emit radio waves as magnetic fields accelerate charged particles. The disk doesn't just shine, it floods the cosmos with energy at nearly every possible wavelength. The efficiency of this process is astonishing. As matter falls inward, gravitational potential energy is converted into heat and radiation. While nuclear fusion in stars turns less than 1% of mass into usable energy, accretion disks around black holes can convert 10% or more of infalling matter's mass into radiant energy. That may sound like a small number, but in astrophysical terms it is staggering. A single gram of material falling into the disk can release more energy than thousands of tons of dynamite. Multiply that by the millions of solar masses worth of gas that a black hole can consume, and the luminosity of quasars like 3C273 begins to make sense. This accretion process is not uniform. The disk can flicker and flare as clumps of matter fall inward, creating the variability that astronomers observe in quasars over timescales of days or weeks. Sometimes a star strays too close, and the black hole tears it apart in a violent tidal disruption event, feeding its remains into the disk and producing bursts of energy. In other cases, dense streams of interstellar gas funnel inward, sustaining the quasar for millions of years at a time. The accretion disk also plays a crucial role in shaping the relativistic jets that emerge from quasars like 3C273. Magnetic fields anchored in the spinning disk twist and coil, channeling some of the inflowing material away from the event horizon and launching it outward at near-light speeds. In this way, the disk is both a furnace of radiation and the launching pad for cosmic jets that extend across thousands of light-years. For astronomers, the study of accretion disks has been one of the most fertile areas of theoretical and observational research in modern astrophysics. Sophisticated computer simulations now model how turbulence, magnetism, and relativity combine to create the luminous fireworks we observe. Observations across the spectrum, from radio telescopes to X-ray satellites, allow researchers to piece together the complex structure of these disks. And 3C273, as the brightest quasar visible from Earth, has been one of the prime targets for these studies, providing a laboratory for testing ideas about how black holes grow and how they release energy into their surroundings. It's a remarkable irony. The most efficient energy engines in the universe are not power plants or stars, but rings of doomed matter circling the abyss. What looks through a telescope like a faint star in Virgo is, in reality, the fiery death dance of matter spiraling into a black hole, its last moments of existence transformed into light that can travel across billions of years to reach our eyes. Without accretion disks, quasars would be invisible. With them, they become the brightest lighthouses in the cosmos. To appreciate just how extraordinary 3C273 really is, we need to place its luminosity into perspective. Numbers in astronomy are so vast that they can feel almost meaningless until they're anchored to familiar benchmarks, our Sun, and then the galaxies that surround us. When astronomers calculated the intrinsic energy output of 3C273, they were forced to confront scales of brightness that dwarfed anything they had ever imagined from a single, compact source. Let's begin with the Sun, the star that sustains life on Earth and represents the most immediate example of radiant energy in our daily existence. The Sun produces about 3.8 times 10 squared watts of energy every second. That's an almost unimaginable number already. In 1 second, the Sun releases more energy than humanity has generated in its entire history. If you were to try to mimic the Sun's output with modern technology, it would be utterly impossible. For us, the Sun feels like the ultimate standard of cosmic power. Now compare that to 3C273. Astronomers estimate that this quasar emits energy equivalent to roughly 2 trillion times the luminosity of the Sun. To put that into perspective, in the time it takes you to blink, 3C273 has released as much energy as the Sun will emit over tens of thousands of years. The difference in scale is almost incomprehensible. But the shock doesn't stop there. Let's step up from stars to galaxies. The Milky Way, our home galaxy, contains about 200 to 400 billion stars. If you add up all their light, the combined luminosity of the Milky Way is about 10 to the power of 1 times that of the Sun. Galaxies are therefore among the brightest structures in the universe, each one glowing like a colossal city of stars across the dark expanse of space. And yet, 3C273, appearing through telescopes as nothing more than a star-like point, emits as much light as an entire massive galaxy, sometimes even more. In other words, one compact region surrounding a black hole, perhaps no larger than our solar system, rivals the collective output of hundreds of billions of stars spread across a galaxy tens of thousands of light-years wide. It's the ultimate cosmic paradox, a tiny point in the sky unleashing more energy than structures millions of times its size. This is what made quasars so hard for astronomers to accept in the early years after 3C-273's discovery. The physics of the 1960s offered no precedent for such concentrated power. Supernovae could briefly outshine entire galaxies, but only for days or weeks. Quasars like 3C-273, by contrast, maintained their brilliance steadily over millions of years. They were not fleeting fireworks but enduring lighthouses powered by something fundamentally different from stars. Another way to appreciate this comparison is by considering energy efficiency. The Sun converts hydrogen into helium through nuclear fusion, releasing less than 1% of the mass as energy. The black hole engine of 3C-273, via its accretion disk, can release up to 10% of the mass energy of matter. That makes quasars the most efficient energy converters known in the universe. No process in stars, planets, or human technology comes even close. And yet, despite this incredible luminosity, 3C-273 is not blindingly bright in our sky. At a distance of 2 billion light-years, its light has been diluted across a sphere of unimaginable size before reaching us. That's why, through a telescope, it looks no different from an ordinary star. But understanding the true scale of its luminosity changes the experience. That faint point of light represents a beacon so powerful it could overwhelm the glow of entire galaxies if placed closer. If 3C-273 were somehow transplanted into the center of the Milky Way, its radiance would turn our night sky into permanent daylight. Earth itself would likely be scorched by the intense radiation, rendering life impossible. Fortunately, its brilliance is tempered by distance, allowing us to study it safely. Thus, when astronomers compare 3C-273 to the Sun or to galaxies, they are not just throwing around big numbers. They are grappling with the reality that the universe contains energy engines that surpass ordinary stellar processes by orders of magnitude. Quasars like 3C-273 are not just brighter than stars, they redefine what brightness can mean in a cosmic sense. The discovery of quasars, beginning with 3C-273, was nothing short of a revolution in astronomy. To understand its impact, it helps to recall the mindset of astronomers in the early 20th century. At that time, the universe already seemed vast. Galaxies were recognized as island universes, each containing billions of stars. The distances to galaxies measured in millions of light-years had already expanded human imagination far beyond what earlier centuries could grasp. Yet even with this enlarged picture, there was still a sense that we were approaching the outer limits of what could exist. The scale of the cosmos felt immense but perhaps finite in its possibilities. Then came quasars. With the identification of 3C-273's redshift in 1963, that comforting sense of scale was shattered. Here was an object that looked like an ordinary star in a telescope, tiny, point-like, unremarkable at first glance. But its spectral fingerprint revealed that it lay billions of light-years away, far beyond the distances of most galaxies then catalogued. That single realization stretched the observable universe in ways few astronomers had dared to imagine. Suddenly, the cosmos wasn't just populated by stars and galaxies. It included hyperluminous beacons that could be seen across a significant fraction of the universe's age and extent. This discovery had profound consequences for how astronomers thought about cosmic distances. Before quasars, the universe was largely studied through galaxies, their shapes, distributions, and clusters. With quasars, astronomers suddenly had objects so bright that they could serve as markers of the universe at epochs when it was only a fraction of its current age. Quasars acted like cosmic lighthouses, illuminating the farthest reaches of space and, by extension, the earliest chapters of cosmic history. 3C-273 was not the most distant quasar by any means, but it was the first, and its existence alone proved that the universe held treasures far more remote and energetic than galaxies alone could provide. The scale shift was not just spatial but also energetic. Galaxies had been considered the largest, brightest structures in the universe. When astronomers realized that quasars outshone entire galaxies while occupying a space no larger than a solar system, the very notion of cosmic energy had to be recalibrated. No longer could astronomers assume that galaxies defined the upper limit of brightness. Now, tiny cores could unleash power rivaling thousands of galaxies. This demanded a new understanding of what objects existed in the cosmos and what processes powered them. Quasars also reshaped cosmology itself, the science of the universe's origin, structure, and evolution. They became crucial evidence that the universe was not static but dynamic and expanding. The extreme redshifts measured in quasars like 3C273 confirmed that not only were galaxies receding from us, but they were doing so at rates corresponding to enormous distances. The universe wasn't just large, it was much larger than many had dared to estimate. And the light from quasars was so ancient that it effectively offered a time machine. To study quasars was to peer back billions of years, closer to the beginning of the cosmos itself. The shockwaves rippled through the astronomical community. Ideas about galactic nuclei, black holes, and cosmic evolution had to be reconsidered or developed from scratch. Where did quasars fit into the life cycles of galaxies? Were they temporary stages in galactic development, or exotic, rare anomalies? Why did they seem so common at great distances, and therefore earlier cosmic times, but rarer nearby? These questions reoriented astronomy away from a static cataloguing of galaxies into a dynamic science of cosmic evolution. It's no exaggeration to say that quasars like 3C273 forced astronomers to accept that the universe was not just vast but layered with epochs of activity, each with its own dominant phenomena. Just as earlier discoveries had displaced Earth from the center of the cosmos, or the Sun from the center of the galaxy, the quasar discovery displaced galaxies themselves from being the ultimate standard of brightness and distance. The scale of the universe had expanded once again, and with it, humanity's sense of place within it. For the public, the impact was just as profound. Newspapers in the 1960s carried stories of these mysterious quasi-stellar objects brighter than galaxies, farther away than anything else then known. The universe, already grand, had suddenly become almost unfathomably vast. 3C273, with its dazzling brightness and its extraordinary distance, became a kind of icon of this new cosmic scale. It symbolized the humbling reality that the more we learn, the larger and stranger the universe becomes. When Martin Schmidt revealed the staggering redshift of 3C273 in 1963, he was not just solving a puzzle about one peculiar object, he was also touching the very heart of cosmology. The universe itself, its expansion, its structure, and its past was suddenly illuminated in a way that had never been possible before. Quasars were not merely exotic curiosities, they were direct, observable evidence for the expanding universe, and they would soon become some of the most powerful tools for probing cosmological questions. To understand why quasars mattered so much, we need to revisit the concept of redshift. Edwin Hubble, decades earlier, had shown that galaxies are receding from us, and that the farther away they are, the faster they move. This relationship, the Hubble law, was one of the first major pieces of evidence for the expanding universe. But by the late 1950s and early 1960s, the evidence was still largely confined to relatively nearby galaxies, on the order of tens or hundreds of millions of light-years. Those distances seemed enormous, yet in cosmological terms they were just the tip of the iceberg. Astronomers had no clear window into the truly early universe, no direct measurements that extended far beyond the local neighborhood of galaxies. Then came quasars. The redshift of 3C273 placed it not hundreds of millions, but billions of light-years away. That meant its light had left the object billions of years earlier, when the universe was much younger. Suddenly, astronomers had access to objects at truly cosmological distances, farther than almost any galaxy observed at the time. Each quasar was a kind of time capsule, its redshift not only confirming that the universe was expanding but also anchoring that expansion across immense stretches of time and space. The very fact that quasars were visible at such distances was revolutionary. If the universe was static or closed off, light from such remote epochs might never reach us. The observation of quasars, shining so brightly across billions of years, was powerful confirmation that the fabric of space itself was stretching, carrying galaxies and quasars ever farther apart. The extraordinary luminosity of 3C273 and its kin was not just an astrophysical oddity, it was evidence written in the language of cosmology. Quasars also helped refine measurements of the Hubble constant, the rate of cosmic expansion. By providing luminous beacons at vast distances, they allowed astronomers to extend the Hubble diagram to scales far beyond ordinary galaxies. This pushed cosmology into a new era, where the universe's expansion could be traced not just locally but across billions of light-years. Even more intriguingly, quasars gave astronomers a way to study the intervening universe. As quasar light traveled through billions of years of cosmic history, it passed through countless clouds of gas, leaving absorption lines in the spectrum. These absorption features, especially the so-called Lyman alpha forest, became direct probes of the intergalactic medium and the distribution of matter across the expanding cosmos. In this way, quasars were not just distant markers but also flashlights shining through the universe, illuminating its structure and confirming its large-scale expansion. For theorists, quasars also had deep implications for the age of the universe. If the universe were too young or too small, it could not plausibly host objects billions of light-years away that had already evolved into such luminous forms. The very existence of 3C273 placed constraints on cosmological models, forcing adjustments to ensure a universe old and vast enough to account for quasars. It is hard to overstate how transformative this was. Before quasars, the expanding universe was a theory supported by galactic redshifts and cosmic microwave background predictions. With quasars, the theory became reality painted across the night sky. Every quasar discovered in the wake of 3C273 confirmed the same pattern. The farther away it was, the greater its redshift, in perfect alignment with an expanding universe. The cosmos was not static, not steady, but dynamic, evolving, and far grander than many had dared to believe. Quasars also raised tantalizing new questions for cosmology. Why were they more common in the distant universe than nearby? This suggested that quasars were tied to an earlier, more active era in cosmic history, perhaps the youth of galaxies, when supermassive black holes were first forming and feeding voraciously. If so, quasars were not just evidence of expansion, they were direct witnesses to galaxy evolution across cosmic time. By studying them, astronomers could piece together a narrative of how galaxies, black holes, and the universe itself grew and changed. In this sense, 3C273 was not merely the first quasar, it was the first unmistakable cosmological lighthouse. Its discovery showed that the expanding universe was not an abstract concept confined to distant galaxies, but a living reality written into every flicker of quasar light. With each photon that arrived from billions of years in the past, it carried a message. The universe is expanding, it has been expanding for eons, and quasars are the cosmic milestones that mark its growth. The moment Schmidt announced that 3C273 spectrum revealed a staggering redshift and placed it billions of light-years away, the astronomical community was thrown into both excitement and turmoil. On one hand, the implications were thrilling, an entirely new class of objects, unimaginably distant, unimaginably bright. On the other hand, the very enormity of those implications made many astronomers uneasy. Could such a thing really be true? Could a single, star-like point really outshine galaxies containing hundreds of billions of stars? The skepticism was immediate, and in some circles, quite intense. Part of the problem was psychological. Astronomers had only just begun to adjust to the idea that galaxies themselves were so large and numerous. That discovery, from Hubble's work in the 1920s, had already expanded humanity's sense of scale dramatically. To then be told that there existed objects far brighter than galaxies, yet so compact that they appeared stellar, seemed absurd. It sounded to many like a violation of common sense. After all, how could something so small in appearance unleash the energy of a galaxy? For decades, astronomers had learned to distrust anything that seemed too extreme or too good to be true. There was also a methodological concern. Redshift, after all, was the key to Schmidt's interpretation. But what if the redshift of quasars didn't mean the same thing it did for galaxies? What if quasars had some exotic internal physics that shifted their spectral lines, creating the illusion of great distance? This alternative explanation became the refuge of many skeptical astronomers. They suggested that quasars might be relatively nearby objects, perhaps within or near our own galaxy, whose unusual emission mechanisms distorted their spectra. If so, there would be no need to assign them absurdly high luminosities or impossible distances. Some even proposed that quasars could be a completely new class of nearby stars, or strange stellar remnants producing exotic radiation. Others leaned on the idea of non-cosmological redshifts, speculating that the spectral shifts could arise from unknown gravitational effects or intrinsic properties of the objects themselves, not the expansion of the universe. In other words, maybe Schmidt's interpretation was simply wrong. This skepticism wasn't baseless. At the time, there were no clear models for how so much energy could be produced in such a small space. Black holes as astrophysical objects were still fringe ideas, regarded more as mathematical oddities than as real, physical engines. Without black holes, there was simply no mechanism powerful enough to make sense of quasar luminosities. Thus, doubting the distance of quasars was, in some ways, more conservative than inventing new physics to explain their brightness. The debates were fierce through the 1960s. Some astronomers clung stubbornly to the idea that quasars had to be local. One famous critic was Holton Opp, who spent much of his career arguing that quasars were not distant at all, but instead physically associated with nearby galaxies despite their high redshifts. He collected images of galaxies that seemed to have quasars near them, suggesting ejections or strange connections. Though most astronomers ultimately rejected these interpretations, they illustrate how uncomfortable many were with the idea of quasars being so far away. For years, papers and conference arguments reflected this divide. On one side, those who accepted the cosmological redshift interpretation, placing quasars at vast distances. On the other, those who sought alternative explanations that preserved a more modest universe. The stakes were enormous because the answer would affect not just our understanding of quasars but the very structure and scale of the cosmos. What eventually eroded the skepticism was the growing weight of evidence. More quasars were discovered, each showing the same kind of extreme redshifts. Their distribution across the sky matched what would be expected of cosmologically distant objects, not of nearby stars. Their variability patterns, their radio structures, and eventually their host galaxies, faintly visible around the brightest quasars with improved telescopes, confirmed that they really were galactic nuclei at cosmological distances. Piece by piece, the case became overwhelming. Yet, in those early years, the doubt was real and justified by the standards of the time. Quasars were simply too shocking to accept without resistance. 3C-273 had cracked open a door to a universe far stranger and more energetic than anyone had anticipated, but not everyone was ready to walk through it. The skepticism, in hindsight, was part of the natural process of scientific discovery. Extraordinary claims require extraordinary evidence, and quasars provided both, but only after years of scrutiny and debate. The early skepticism surrounding 3C-273 gradually began to fade as more quasars were discovered, each reinforcing the idea that these objects were indeed at enormous distances and not merely odd local stars. The confirmation process was gradual but compelling, as multiple lines of evidence converged to support the cosmological interpretation of their redshifts. What initially appeared to be a single, anomalous object became the first in a growing population of quasi-stellar sources, all exhibiting the same puzzling combination of extreme luminosity, star-like appearance, and high redshift. The discovery of additional quasars in the years following 1963 was rapid, thanks in large part to advances in radio astronomy. The third Cambridge catalogue of radio sources, 3C, had already revealed dozens of bright radio sources, but only a few had been matched to optical counterparts. As spectroscopic techniques improved and more of these counterparts were studied, astronomers found that many exhibited spectral lines that could be explained only by significant redshifts, similar to or even exceeding that of 3C-273. Each new quasar confirmed that Schmidt's interpretation was not a fluke. They all pointed toward the same conclusion. These were immensely luminous, compact objects residing at cosmological distances. One of the pivotal moments came with the discovery of quasars with even higher redshifts than 3C-273. Some of these objects were found with redshifts approaching Z equals 2 or 3, placing them more than 10 billion light-years away. This was astonishing. It meant that quasars were not just rare, nearby oddities, but a widespread population visible from across almost the entire observable universe. The pattern of increasing redshift with distance matched the predictions of the expanding universe model. As more quasars were catalogued, the redshift-distance relationship held consistently, providing powerful independent confirmation of the cosmological interpretation. Spectroscopic studies of these new quasars consistently revealed broad emission lines, often from hydrogen, carbon, magnesium, and other elements. The widths and intensities of these lines indicated not only high velocities within the emitting regions but also reinforced the interpretation of extreme distances. Variability studies added further weight. The rapid flickering of quasar brightness implied that their emitting regions were compact, consistent with a central supermassive black hole rather than a sprawling, nearby star cluster. Together, these characteristics became the defining hallmarks of quasars and strengthened the case that they were indeed distant, energetic phenomena rather than local oddities. Radio interferometry played a key role in confirming their distances as well. By mapping the structure of quasars at radio wavelengths, astronomers were able to resolve jets and lobes on scales that implied immense physical sizes when corrected for cosmological distance. If these sources were nearby, the jets would be microscopic. Instead, they stretched across tens of thousands of light-years, consistent with the enormous distances indicated by their redshifts. The geometry and behavior of these radio structures left little doubt that quasars were not just star-like, energetic spots in our galaxy but truly extragalactic and cosmologically remote. Optical imaging eventually revealed faint host galaxies around the brightest quasars, including 3C273 itself. These galaxies, often elliptical in shape, confirmed that the quasars were located at the centers of galaxies billions of light-years away. Before these images were available, one could still speculate that quasars were unusual objects nearby. With the host galaxies in view, that speculation became untenable. The redshift interpretation was no longer just plausible, it was compelling. The pattern of discovery also helped address one of the early criticisms, the idea that redshifts might be intrinsic to quasars rather than cosmological. As more quasars were mapped across the sky, their distribution appeared isotropic, showing no preferential association with nearby galaxies. The further away a quasar appeared to be, the higher its redshift, a clear correlation that could be explained only by cosmic expansion. The intrinsic redshift hypothesis lost credibility, replaced by the now standard view that quasar redshifts are primarily due to the universe stretching the wavelengths of their light across billions of years. The expanding catalogue of quasars also helped astronomers understand the evolution of the universe. They noticed that quasars were far more common at higher redshifts, meaning that they were more abundant in the early universe. This suggested that quasars were not eternal objects but rather transient phases in galactic evolution, associated with periods of intense black hole feeding and star formation. In this way, the confirmation of quasars not only cemented their distances but also began to provide insight into the life cycles of galaxies and the growth of supermassive black holes over cosmic time. By the mid-1970s, the accumulation of discoveries, spectroscopic redshifts, variability data, radio jet measurements, and faint host galaxies left little room for doubt. Quasars were confirmed as extragalactic, incredibly luminous, and cosmologically significant objects. 3C273, as the first identified quasar, retained its symbolic role, but it was now clearly part of a much larger population that was reshaping astronomy's understanding of the universe's scale, energy distribution, and evolutionary history. 3C273 quickly transcended the confines of academic journals and observatories to become a symbol in popular science and astronomy circles. Before quasars were widely understood, 3C273 stood as a beacon of cosmic mystery, a star-like point in Virgo that defied all conventional understanding. Its fame stemmed not only from being the first identified quasar but also from the striking contrast between its unassuming appearance in the night sky and the extraordinary physics it represented. In the 1960s and 1970s, science magazines and newspapers began featuring stories about the quasi-stellar radio sources, highlighting their unimaginable distances and staggering luminosities. 3C273 became the poster child of these stories. Writers and science communicators were drawn to its paradoxical nature. It looked like a tiny, ordinary star but unleashed the energy of an entire galaxy. For the public, it was both fascinating and slightly terrifying, a glimpse into a universe more extreme than anything in everyday experience. Astronomers themselves often referred to it informally by its catalogue designation, 3C273, which in time became instantly recognizable among professionals as shorthand for the archetypal quasar. The notoriety of 3C273 also owed much to its accessibility to amateur astronomers. While most quasars require large telescopes and sensitive detectors to be observed, 3C273 is visible with modest amateur instruments under dark skies. This accessibility created a bridge between professional and amateur astronomy. A backyard astronomer could locate Virgo, identify a faint point of light, and know that they were seeing the very first quasar ever discovered, a direct connection to cutting-edge science. This tangible engagement made 3C-273 almost a celebrity in stargazing circles. Its significance in popular science extended beyond mere visibility. 3C-273 became a symbol of the unknown in the universe, representing the incredible scale, age, and energy of cosmic phenomena. It was cited in books and lectures as an example of how the universe could surprise even seasoned scientists. The phrase "as bright as a galaxy but looks like a star" became a standard way of communicating the paradox of quasars to students and the general public. It captured the imagination because it was easy to visualize yet hard to fully comprehend, an object small enough to appear point-like but vast in its power. Even educational programs and planetarium shows used 3C-273 as a storytelling tool. The story of its discovery, radio waves picked up from a distant constellation, a visible counterpart painstakingly identified, the spectral analysis revealing its redshift, and the realization of its enormous energy output, made for compelling narrative. It exemplified the scientific process: observation, hypothesis, debate, and eventual understanding. Children, students, and amateur enthusiasts were able to connect with the mystery and the drama of discovery, giving 3C-273 a place in the cultural imagination of science beyond the purely academic. 3C-273's popularity in science circles was also reinforced by the very human drama surrounding its discovery. Martin Schmidt's breakthrough came after meticulous work on spectral lines that seemed incomprehensible at first. The object's brightness and distance challenged prevailing assumptions, creating a narrative of intellectual tension and eventual triumph. Stories of skeptical astronomers debating whether such an object could exist were frequently recounted, turning 3C-273 into more than a technical achievement. It became an emblem of curiosity, perseverance, and the occasional audacity required in scientific inquiry. Over time, the designation 3C-273 became shorthand for the broader phenomenon of quasars. While new quasars were discovered in increasing numbers, none captured public or professional attention quite like the first one. It remained a touchstone in lectures, textbooks, and documentaries, a reference point for discussions about supermassive black holes, relativistic jets, and the extreme scales of the universe. Even when thousands of quasars had been catalogued, 3C-273 retained a special status as the object that opened the door to understanding this previously hidden realm of the cosmos. Its role as a symbol extended into the imagination of scientists themselves. To astronomers, 3C-273 represents the universe at its most energetic, most extreme, and most unknowable. It embodies the paradoxes that drive research, objects that challenge our understanding, demand new physics, and stretch the limits of observation. In that sense, 3C-273 is not just an astronomical object. It is a cultural icon within science, a reminder of the universe's capacity for mystery and the human drive to uncover it. The story of 3C-273 becomes even more compelling when one considers that it is not just a point of visible light. It is a cosmic powerhouse radiating across the entire electromagnetic spectrum. Studying it in multiple wavelengths has provided a layered understanding of the physics at work in quasars, revealing aspects that a single band alone could never show. Astronomers soon realized that to truly comprehend 3C-273, it was necessary to observe it across radio, optical, ultraviolet, X-ray, and even gamma-ray bands, a strategy that would come to define modern astrophysics. Radio astronomy was, in fact, where 3C-273's story began. The initial discovery in the 1950s came from the third Cambridge catalogue of radio sources, which recorded a strong radio signal from a point in the sky within the constellation Virgo. These radio waves revealed that the object was energetic even before its optical counterpart was identified. Follow-up observations using radio interferometry allowed astronomers to resolve the structure of the source, including the faint, elongated jet extending from the core. The radio data demonstrated that quasars are not uniform blobs of light but dynamic systems with large-scale structures extending far beyond the central nucleus. In the optical band, 3C-273 was identified as a point-like star, the very object Schmidt analyzed spectroscopically. Optical spectroscopy revealed the redshift of its spectral lines, allowing astronomers to calculate its distance and intrinsic luminosity. Detailed optical imaging over the decades has also unveiled the faint host galaxy surrounding the quasar, showing that quasars reside at the centers of massive galaxies. Observations in optical and near-infrared bands provide crucial information about the accretion disk, the jets, and the environment immediately surrounding the black hole. Subtle variability in optical brightness over days or weeks offered additional insights into the compactness of the emitting region and the processes powering the quasar. X-ray observations added an entirely new dimension to our understanding of 3C273. Satellites such as Einstein, Rosat, and Chandra revealed that quasars emit prodigiously in high-energy X-rays. These X-rays originate from the innermost regions of the accretion disk, near the event horizon of the supermassive black hole, and also from shocks in the relativistic jets. X-ray observations allowed astronomers to probe regions that are impossible to study optically, revealing extreme temperatures, relativistic particle acceleration, and magnetic interactions at play close to the black hole. The high-energy radiation confirmed that quasars are powered by fundamentally different processes than stars, as no stellar source can produce such intense X-ray flux over a compact region. Gamma-ray studies, conducted with satellites such as FEMI and the Compton Gamma Ray Observatory, revealed even more extreme processes. In gamma rays, the jets and high-energy particles accelerate to relativistic velocities, producing emissions that reach the highest energies detectable. Gamma-ray observations of 3C273 showed that the jet not only emits visible and radio light but also channels energy into highly energetic photons, indicating particle acceleration mechanisms that remain active over vast distances from the black hole. The detection of gamma rays also underscores the efficiency and power of the black hole engine, as the conversion of matter to energy reaches its upper limits in these bands. Observing 3C273 across multiple wavelengths provides complementary insights. Radio waves trace the extended jets and lobes, optical light maps the accretion disk and host galaxy, X-rays probe the inner disk and jet shocks, and gamma rays reveal the highest energy processes in the relativistic outflows. By combining these observations, astronomers can create a holistic picture of the quasar: how matter flows into the black hole, how magnetic fields channel material into jets, and how radiation escapes across the universe. Multi-wavelength studies also help model the energy output of the quasar and understand the mechanisms behind its variability, which is observed in all bands but on different timescales and amplitudes. The multi-wavelength approach has transformed 3C273 into one of the most thoroughly studied quasars in the universe. It serves as a benchmark for understanding other quasars, many of which are too faint to study in such detail. The combination of radio, optical, X-ray, and gamma-ray observations allows astronomers to probe scales from the entire galaxy down to the event horizon of the black hole, something impossible in most other extragalactic sources. Each wavelength tells a different part of the story, and together they reveal the complexity and power of this cosmic engine. Ultimately, the study of 3C273 across the spectrum illustrates the evolution of modern astronomy itself. It shows how advances in technology, from radio dishes to space-based X-ray and gamma-ray telescopes, can uncover new layers of reality, each revealing a different aspect of the same object. This multi-wavelength perspective not only confirmed the extraordinary nature of 3C273 but also provided a model for how astronomers would study the most energetic and distant objects in the universe for decades to come. One of the most intriguing characteristics of quasars, including 3C273, is their variability, an unpredictable flickering in brightness that occurs across multiple wavelengths. Unlike ordinary stars, which generally maintain a steady output over long periods, quasars can change their luminosity on timescales ranging from hours to years. This variability was one of the earliest clues that the sources of quasar energy are extremely compact and dynamic, and studying it has provided invaluable insight into the inner workings of these cosmic powerhouses. 3C273 was among the first quasars observed to exhibit such variability. Early optical monitoring revealed that its brightness could fluctuate by a few tenths of a magnitude over the course of days or weeks. While these changes might seem subtle when expressed numerically, they are significant for an object billions of light-years away. The fact that such a distant object could vary in brightness on such short timescales suggested that the emitting region must be relatively small, because light from different parts of a larger object would smear out any rapid changes. This observation was consistent with the idea that the bulk of the quasars' light comes from the accretion disk around a supermassive black hole rather than from a vast number of stars. Variability is not limited to optical light. 3C273 has also been observed to fluctuate in radio, ultraviolet, X-ray, and gamma-ray bands. Each of these bands offers a window into different parts of the quasar. Radio variations often reflect changes in the relativistic jets, including the formation of bright knots or shocks moving outward along the jet. Ultraviolet and optical flickering primarily trace processes in the accretion disk, such as instabilities or turbulence in the inflowing material. X-ray and gamma-ray variations probe the innermost regions, near the event horizon, revealing rapid changes in the most energetic processes surrounding the black hole. The patterns of variability can also be periodic or quasi-periodic in some cases, providing a probe of physical structures in the disk and jet. For example, rotating hot spots or magnetic reconnect ion events in the accretion disk may produce regular fluctuations in brightness, while the emergence of relativistic plasma blobs along the jet can cause bursts of emission that propagate across multiple wavelengths. Observing these changes simultaneously across bands allows astronomers to construct a timeline of energy release, tracing matter as it spirals inward, heats, radiates, and sometimes is ejected in the jet. The variability of 3C273 has also been critical in estimating the size of its emitting regions. Rapid flickering indicates that light from the varying region cannot take longer to reach us than the timescale of the brightness changes. For instance, if the quasar brightens over a period of a few days, the region responsible for that emission must be light days in diameter, a size comparable to the solar system rather than an entire galaxy. This insight was essential in linking the energy output of quasars to supermassive black holes and accretion disks, as it confirmed that the immense luminosity is concentrated in a very compact area. Another important aspect of quasar variability is that it provides clues about the mechanisms driving energy release. In 3C273, the variability patterns suggest that turbulence, magnetic fields, and instabilities in the accretion disk play major roles. Magnetic reconnect ion events, where twisted magnetic field lines suddenly snap and release enormous amounts of energy, may be responsible for sudden flares, particularly in X-ray and gamma-ray bands. Similarly, the motion of plasma blobs along the relativistic jet can produce bursts of emission as the material interacts with shocks and magnetic fields. By tracking these variations over time, astronomers can probe physics that cannot be replicated in laboratories on Earth. Long-term monitoring has also revealed that quasar variability is not purely chaotic. Some quasars, including 3C273, show patterns of gradual brightening or dimming over years to decades, possibly reflecting changes in the rate at which material falls onto the black hole. These secular trends help scientists understand the feeding habits of supermassive black holes and the evolution of the host galaxy environment. In a sense, quasars are cosmic diaries, recording the dynamic history of matter falling into the black hole and energy propagating outward into the surrounding galaxy and intergalactic space. The variability of 3C273, observable across multiple wavelengths and timescales, also makes it an ideal target for coordinated observational campaigns. Modern instruments, from optical telescopes to space-based X-ray and gamma-ray observatories, have tracked its fluctuations simultaneously, allowing astronomers to correlate events across the spectrum. These campaigns have helped map the structure of the quasar in unprecedented detail, linking the inner accretion disk, relativistic jets, and broader galactic environment into a unified picture. In summary, the flickering of 3C273 is more than a curiosity. It is a diagnostic tool. Each flare, dip, or periodic change carries information about the physics near a supermassive black hole, the behavior of the accretion disk, and the dynamics of relativistic jets. Variability transforms what appears to be a steady star-like point into a dynamic, living system, providing a window into processes occurring on scales and energies far beyond anything we can reproduce on Earth. By studying these fluctuations, astronomers have not only confirmed the nature of quasars but also gained a deeper understanding of the extreme forces shaping the universe. One of the most striking and enigmatic features of 3C273 is its relativistic jet, a narrow, highly collimated stream of plasma that shoots out from the quasar at velocities approaching the speed of light. This jet, extending tens of thousands of light-years from the central black hole, is not only visually spectacular but also scientifically invaluable, providing a natural laboratory for studying extreme physics that cannot be replicated on Earth. Understanding the physics of these jets is essential to grasping how quasars interact with their surrounding environments and how they channel energy across intergalactic space. Relativistic jets are formed in the immediate vicinity of a supermassive black hole, where the accretion disk and intense magnetic fields play crucial roles. The material spiraling into the black hole does not simply disappear quietly across the event horizon. Instead, a fraction of it is captured by twisted magnetic fields near the poles of the black hole and accelerated outward at speeds close to the speed of light. The physics of this process involves a combination of general relativity, magnetohydrodynamics, and particle acceleration. Magnetic field lines anchored in the rotating accretion disk or spinning black hole become tightly wound, creating tension. As the lines snap or realign, they launch charged particles along the rotation axis, forming the narrow, powerful jet. 3C-273's jet is visible across multiple wavelengths: radio, optical, X-ray, and even ultraviolet, each providing unique information about the energy and composition of the outflowing material. In radio observations, the jet appears as a bright, elongated feature extending from the quasar, sometimes terminating in large lobes where the plasma interacts with intergalactic gas. The optical component of the jet, though faint compared to the quasar core, reveals knots of accelerated particles that glow due to synchrotron radiation. Electrons spiraling around magnetic field lines at nearly light speed emit energy across the electromagnetic spectrum. In X-rays, the jet becomes a probe of extremely high-energy processes, including shocks that reaccelerate particles and magnetic reconnect ion events, demonstrating the sheer power contained within these narrow beams. A key feature of relativistic jets is that their high speeds give rise to relativistic effects such as Doppler boosting. When a jet is pointed toward Earth, the emitted light is amplified, making the jet appear brighter than it would if seen side-on. This effect explains why 3C-273's jet, despite being faint in most telescopes, can still be detected in optical images and even by careful amateur observers under favorable conditions. Relativistic beaming also affects the apparent motion of features within the jet, sometimes producing the illusion that knots of plasma move faster than the speed of light, a phenomenon known as superluminal motion, which is a direct consequence of geometry and relativistic speeds, not a violation of physics. The study of 3C-273's jet has provided essential insights into particle acceleration mechanisms in extreme environments. The knots observed along the jet indicate localized regions where electrons are accelerated to energies billions of times higher than those produced in terrestrial particle accelerators. Magnetic turbulence, shock waves, and reconnect ion events are all thought to contribute to these accelerations, and the emission we observe across wavelengths acts as a diagnostic tool for understanding these mechanisms. By studying the jet, astronomers can test models of plasma physics under conditions that are otherwise inaccessible, providing a bridge between theoretical predictions and observable reality. Jets also play a fundamental role in the evolution of galaxies. The energy and momentum carried by the jet from 3C-273 can influence the intergalactic medium, heating gas, triggering or suppressing star formation, and redistributing matter across tens of thousands of light-years. In this way, relativistic jets are not mere byproducts of black hole feeding. They are agents of cosmic feedback, shaping the growth and structure of galaxies over millions of years. 3C-273's jet, because of its brightness and proximity relative to more distant quasars, has become a prototype for understanding these feedback processes in active galactic nuclei. Moreover, the combination of multi-wavelength monitoring and high-resolution imaging of 3C-273's jet allows astronomers to study time-dependent processes. Observing how the brightness and morphology of the jet changes over months or years provides insight into the dynamics of relativistic flows, the evolution of shock fronts, and the interaction of plasma with surrounding material. By connecting these observations with theoretical models, scientists can simulate the behavior of relativistic jets and refine our understanding of extreme astrophysical plasmas. In summary, 3C-273's jet is far more than an aesthetic feature. It is a window into physics at the limits of energy, velocity, and magnetism. It illustrates how matter and energy can be accelerated and transported across immense distances, how black holes influence their surroundings, and how some of the most extreme processes in the universe manifest visibly across the cosmos. By studying this jet, astronomers have gained critical knowledge about relativistic flows, magnetic field dynamics, particle acceleration, and the interplay between supermassive black holes and their host galaxies, a legacy that began with the identification of 3C-273 itself. 3C-273's role in radio astronomy goes far beyond its initial discovery as a radio source. It became a cornerstone for calibrating and testing the very instruments that first revealed it. When radio astronomers in the 1950s and 1960s began mapping the sky, one of the major challenges they faced was ensuring that their instruments were accurately measuring flux, position, and structure. Reliable calibration sources were scarce, particularly those that were bright, compact, and well characterized. 3C-273 fit the bill perfectly, making it a natural standard against which other observations could be benchmarked. The first step in using 3C-273 as a calibration source was its remarkable stability in radio flux. While its optical and X-ray emissions could vary over days and months, its radio output, especially over longer periods, was sufficiently stable for telescope calibration purposes. By observing a source with a known flux, radio astronomers could adjust their instruments to ensure that the measurements of other, less well-known sources were accurate. This was especially important in the early days of radio interferometry, when arrays of multiple telescopes had to be precisely synchronized to produce clear images. 3C-273 became a dependable reference point in these experiments. Its brightness was another key advantage. With a relatively strong radio flux, 3C-273 could be detected easily even with mid-sized radio dishes. This meant that observatories around the world could use it as a common benchmark, regardless of their telescope size. By comparing measurements of 3C-273 taken at different observatories, astronomers could cross-calibrate their instruments, ensuring consistency in data across the global radio astronomy community. This process was essential for building the confidence needed to interpret faint and distant radio sources, which would otherwise be difficult to quantify accurately. The compactness of 3C-273 in radio wavelengths also played a crucial role. Unlike extended radio galaxies with diffuse lobes, 3C-273 presents a core that is relatively point-like at radio frequencies. This characteristic makes it ideal for measuring the resolution and beam shapes of radio telescopes, testing how well an array can distinguish closely spaced sources. By observing 3C-273 under controlled conditions, engineers could fine-tune antenna alignments, calibrate phase and amplitude measurements in interferometers, and verify that the synthesized images accurately represented reality. In addition to its use as a calibration source, 3C-273 also served as a testbed for developing new radio astronomy techniques. Early Very Long Baseline Interferometry (VLBI) experiments, which link widely separated radio antennas to achieve extraordinary spatial resolution, relied on bright, compact quasars like 3C-273 to refine their methods. Observing its core and jet allowed astronomers to measure fringe patterns, timing delays, and other instrumental effects that were critical for producing high-resolution radio maps. Without such well-characterized sources, the development of VLBI and other advanced radio techniques would have been much slower. Even today, 3C-273 remains an essential calibration source in radio astronomy. Modern facilities, including the Very Large Array (VLA) in New Mexico and the European VLBI network, continue to use it as a standard reference. Its known flux density across multiple radio bands allows astronomers to calibrate not just brightness but also polarization, an increasingly important measurement in studies of magnetic fields in jets and interstellar medium. The combination of brightness, stability, and compactness makes 3C-273 a gold standard for radio observations, bridging the gap between early discoveries and cutting-edge modern research. The quasar's role in calibration also highlights an often overlooked aspect of astronomy: the reliance on anchor points to make sense of the universe. Without bright, stable sources like 3C-273, radio observations of distant galaxies, pulsars, or even other quasars would lack reliability. 3C-273, therefore, is not just a remarkable object in its own right. It has also played a foundational role in ensuring that the tools we use to explore the cosmos are precise and trustworthy. In a sense, every radio map of the sky owes a debt to this first quasar, whose discovery inadvertently provided astronomers with a cosmic measuring stick. Even decades after its discovery, 3C-273 continues to play a vital role in modern cosmology and astrophysics. Its significance has evolved from being merely the first identified quasar to serving as a detailed laboratory for understanding some of the most fundamental processes in galaxy evolution, supermassive black hole growth, and the behavior of matter under extreme conditions. Unlike many distant quasars that are too faint or too small to study in detail, 3C-273's relative proximity and extraordinary brightness allow astronomers to probe both its central engine and its interaction with the surrounding galaxy. One of the primary ways 3C-273 informs modern cosmology is by providing a window into the growth of supermassive black holes. The mass of its central black hole is estimated to be on the order of several hundred million solar masses. By studying the accretion rate, luminosity fluctuations, and jet dynamics of 3C-273, astronomers can infer how black holes accumulate matter over cosmic time. Observing these processes in a nearby, bright quasar allows researchers to test models of black hole feeding efficiency, accretion disk structure, and relativistic jet launching, phenomena that are critical to understanding the evolution of black holes across the universe. Moreover, 3C-273 serves as a benchmark for studying the relationship between black holes and their host galaxies. It has been observed that supermassive black holes are intimately connected to the properties of their host galaxies, including mass, stellar population, and central bulge structure. By analyzing 3C-273 and its faint surrounding host galaxy, astronomers can explore how black hole growth correlates with galactic development. For example, the energy output from the quasar, including radiation and jets, likely influences star formation in the host galaxy, regulating the growth of both the black hole and the galactic environment. This feedback mechanism is now considered a central element in models of galaxy evolution. 3C-273 is also critical in the study of cosmic chemical enrichment. The broad emission lines in its spectrum reveal the presence of elements like carbon, nitrogen, oxygen, and iron, allowing astronomers to assess the composition of gas in the early universe. By comparing these chemical abundances to those in other quasars at varying redshifts, scientists can trace the buildup of heavy elements over cosmic time, providing insight into the star formation history and the evolution of galaxies that seeded this enriched material. The jet of 3C-273 continues to provide an unparalleled laboratory for high-energy astrophysics and galaxy feedback studies. Modern observations using radio interferometry, optical imaging, and X-ray telescopes probe how the jet interacts with the surrounding intergalactic medium. These interactions can heat gas, trigger or suppress star formation, and redistribute energy across vast distances. By studying the jet structure, variability, and particle acceleration mechanisms, astronomers can refine models of jet-driven galaxy evolution, a process believed to have shaped the growth of massive galaxies throughout cosmic history. 3C-273 also serves as a calibration point and reference for cosmological surveys. Its well-characterized redshift, multi-wavelength luminosity, and proximity make it a standard against which the properties of more distant, less accessible quasars are measured. By using 3C-273 as a template, astronomers can estimate the physical characteristics of thousands of other quasars across the sky, extending our understanding of the cosmic population as a whole. Furthermore, its proximity and brightness allow for long-term monitoring campaigns, which are invaluable for studying black hole accretion physics and jet evolution in real time. Variability studies across optical, X-ray, and gamma-ray bands help refine theoretical models of disk instabilities, relativistic particle acceleration, and magnetic field interactions. These insights can then be applied to distant quasars, where such detailed measurements are not feasible, effectively using 3C-273 as a Rosetta Stone for understanding the quasar phenomenon throughout cosmic history. The quasar also plays a role in the study of cosmological parameters and the large-scale structure of the universe. Observations of absorption lines in its spectrum provide information about intervening gas clouds and the intergalactic medium. These data help map the distribution of matter along the line of sight and offer indirect constraints on models of cosmic evolution, galaxy formation, and the growth of structure in the universe. In essence, 3C-273 is no longer just the first quasar. It is a full-fledged laboratory for modern astrophysics. Its study informs multiple branches of cosmology: black hole growth, jet physics, galaxy evolution, chemical enrichment, and the large-scale structure of the universe. By acting as both a benchmark and a detailed case study, it continues to shape our understanding of how galaxies and black holes evolve over billions of years. Even with thousands of other quasars discovered since 1963, none provides the combination of brightness, accessibility, and well-studied history that makes 3C273 so uniquely valuable for modern cosmology. The study of 3C273 remains profoundly important today, even though thousands of quasars have been discovered since its identification in 1963. Its significance lies not just in its historical role as the first confirmed quasar, but in the unique combination of characteristics that make it an unparalleled natural laboratory for understanding the universe's most energetic phenomena. While newer quasars often provide additional data points, few are as bright, nearby, and accessible across the electromagnetic spectrum as 3C273, making it a benchmark against which all other quasars are measured. One key reason 3C273 still matters is its brightness and proximity. Most quasars, while more numerous, are much fainter and more distant, making detailed study difficult. Observing the faintest quasars requires long exposures, highly sensitive instruments, or both, limiting the ability to explore their structure and variability in depth. 3C273, by contrast, shines intensely across radio, optical, ultraviolet, X-ray, and gamma-ray wavelengths. This accessibility allows astronomers to conduct high-resolution imaging, time-resolved spectroscopy, and multi-wavelength monitoring that is impossible for many other quasars. In other words, 3C273 acts as a fully accessible model system, a quasar in a laboratory for studying phenomena that are otherwise only observable at cosmic distances. Its historic role also gives it a foundational place in the narrative of astrophysics. 3C273 was the object that forced the astronomical community to confront the existence of extremely luminous, compact objects at cosmological distances. Understanding its discovery and the subsequent debates surrounding redshift interpretation, energy output, and variability helps scientists and students appreciate the evolution of astrophysical knowledge. By revisiting 3C273, researchers can trace the development of theoretical frameworks for quasars, black holes, and galaxy evolution. It serves as both a scientific and pedagogical touchstone, illustrating how empirical data, careful observation, and rigorous analysis combine to challenge existing paradigms. Another reason 3C273 remains vital is its role in testing and refining theoretical models. Because it is bright and well characterized, it provides a benchmark against which models of black hole accretion, jet formation, and relativistic plasma physics can be evaluated. The detailed data available from decades of observations enable comparisons between predicted and observed behaviors, including luminosity variations, jet kinematics, and spectral energy distributions. In effect, 3C273 allows astrophysicists to validate their theories in a regime of extreme energy and gravity, conditions that are otherwise impossible to reproduce or study with other quasars due to distance or faintness. The quasar's variability further underscores its continued importance. Long-term monitoring campaigns have tracked changes in brightness and spectral characteristics over decades, providing insight into accretion processes, jet dynamics, and magnetic field interactions in real time. While other quasars can be observed for variability, 3C273's combination of proximity, luminosity, and multi-wavelength detectability makes it uniquely suited for such studies. It allows scientists to observe processes on human observable timescales rather than relying solely on snapshots of distant, faint objects. 3C273 is also critical for understanding the interaction between supermassive black holes and their host galaxies. Its relativistic jet and the surrounding environment provide a detailed case study in how energy feedback shapes galactic evolution. While other quasars also exhibit jets, few allow for such precise mapping of jet structure, energy transport, and host galaxy interactions across multiple wavelengths. Studying 3C273 informs models of feedback mechanisms, which are crucial for explaining why galaxies grow the way they do, how star formation is regulated, and how supermassive black holes and galaxies co-evolve over billions of years. In addition, 3C273 serves as a calibration standard and reference point for modern astronomy. Its well-known flux, spectral features, and jet characteristics allow it to be used as a benchmark for both ground-based and space-based observatories. This is particularly important as new instruments, such as next-generation radio arrays and space telescopes, are developed. Having a reliable, well-characterized source ensures that measurements across the universe remain consistent and accurate. Finally, 3C273 has symbolic significance. It embodies the human drive to understand extremes in the cosmos, the brightest, the most distant, the most energetic. Studying it reminds astronomers and the public alike that discoveries are not just about numbers or catalogue entries, but about expanding the limits of knowledge and confronting phenomena that challenge our understanding of physics and the universe. Even in a universe now known to contain thousands of quasars, 3C273 remains a gateway to exploration, the first door that opened onto an extraordinary realm of cosmic power and mystery. In essence, the first quasar still matters because it is bright, accessible, historically foundational, scientifically rich, and symbolically profound. Its continued study allows astronomers to refine theoretical models, probe the physics of extreme environments, understand galaxy black hole co-evolution, and test observational techniques, all while linking contemporary research to the very origins of quasar discovery. It is both a reference point and a source of new insight, demonstrating that the first discovery often remains the most informative. The future of studying 3C273 promises to be as exciting as its past. With the advent of next-generation telescopes and radio arrays, astronomers are poised to probe this iconic quasar in unprecedented detail, revealing aspects of its structure, evolution, and energetic processes that were previously inaccessible. These new observational capabilities will allow scientists to push the boundaries of what is known about supermassive black holes, relativistic jets, and the environment surrounding active galactic nuclei. The James Webb Space Telescope, JWST, with its extraordinary infrared sensitivity and high-resolution imaging, represents a major leap forward in studying 3C273. Infrared observations can penetrate dust that obscures parts of the quasar and its host galaxy, providing a clearer view of the galactic core and the regions immediately surrounding the black hole. JWST can help astronomers resolve the structure of the accretion disk and detect faint features in the host galaxy that were previously invisible. By capturing light that has been redshifted into the infrared, JWST will also allow scientists to examine the distribution of older stars and dust, giving insights into the evolutionary history of the galaxy hosting 3C273. This could reveal how the growth of the black hole is linked to the assembly of the surrounding galaxy over cosmic time. Spectroscopy with JWST will also provide critical chemical information. The telescope can detect faint emission and absorption lines in the infrared that trace elements such as carbon, oxygen, nitrogen, and iron. Studying these lines in detail will help astronomers understand the metallicity of the quasar's environment and the history of star formation in its host galaxy. This data can be compared with other distant quasars to build a broader picture of how chemical enrichment proceeds in galaxies harboring supermassive black holes, offering clues about the interplay between black hole activity and galactic evolution. In the radio domain, new arrays like the Square Kilometre Array, SKA, and upgrades to existing instruments such as the Very Large Array, VLA, will transform our understanding of 3C273's jet and the surrounding intergalactic medium. With unprecedented sensitivity and resolution, these arrays can map the fine structure of the jet, revealing shocks, knots, and turbulence at scales that were previously unresolved. This will allow astronomers to study how energy and particles are transported from the central black hole into intergalactic space, providing a detailed view of jet physics and the feedback mechanisms that influence galaxy formation. Moreover, these radio arrays can measure polarization in the jet with exquisite precision. Polarization studies reveal the orientation and strength of magnetic fields, which are central to the formation and collimation of relativistic jets. By observing 3C273 at multiple radio frequencies over time, astronomers can construct three-dimensional models of the magnetic environment, track the evolution of magnetic structures, and better understand how these fields accelerate particles to near-light speeds. High-energy observatories, both current and forthcoming, will continue to probe the innermost regions of 3C273. Next-generation X-ray telescopes like Athena and gamma-ray observatories will track rapid variability near the black hole, examine the mechanisms of particle acceleration in jets, and detect high-energy flares that provide direct information about relativistic plasma dynamics. Combining these observations with optical, infrared, and radio data will allow multi-wavelength studies of unprecedented depth, effectively creating a time-resolved, multi-layered picture of the quasar. In addition, long-term monitoring campaigns with new telescopes will help resolve outstanding questions about quasar variability and black hole feeding cycles. Observing 3C273 over months, years, and even decades will allow astronomers to see how accretion rates change, how jet structures evolve, and how these processes are coupled to the larger galaxy. The combination of high-resolution imaging, spectroscopy, and time-domain observations will provide a more complete understanding of the physics driving this extraordinary object. Finally, these future observations of 3C273 will serve as a benchmark for interpreting more distant, fainter quasars. By studying a nearby, bright quasar in exquisite detail, astronomers can refine models that are then applied to quasars at the edge of the observable universe. This comparative approach will help unravel the history of black hole growth, the evolution of galaxies, and the large-scale structure of the universe. 3C273 will continue to act as a Rosetta Stone for understanding the energetic phenomena that have shaped cosmic history for billions of years. In essence, future telescopes and radio arrays promise to illuminate every aspect of 3C273, the inner workings of its black hole, the structure and dynamics of its jet, the composition and evolution of its host galaxy, and the interplay of these elements over cosmic timescales. While it has already revolutionized our understanding of the universe, the quasar story is far from complete, and the coming decades of observation will undoubtedly reveal layers of complexity and insight that have never before been accessible. The discovery of 3C273 stands as one of the most transformative moments in modern astronomy, a revelation that forever expanded our perception of the universe and the forces at work within it. Before its identification, the cosmos was understood largely in terms of stars, galaxies, and nebulae, with energy outputs that were comparatively modest and predictable. 3C273 shattered those assumptions. Here was a single point of light, appearing as unremarkable as a distant star, yet releasing more energy than an entire galaxy. Its existence forced astronomers to confront phenomena of extreme scale, energy, and complexity, revealing a universe far more dynamic and violent than previously imagined. In a sense, 3C273 opened a window into the early universe. The light we see today left the quasar billions of years ago, providing a direct glimpse into the conditions and processes that prevailed when the cosmos was young. Its study allows astronomers to trace the growth of supermassive black holes, the assembly of galaxies, and the enrichment of the intergalactic medium with heavy elements at epochs that are otherwise difficult to probe. Each photon from 3C273 carries a story from the distant past, enabling researchers to reconstruct the history of cosmic structure and energy distribution across billions of years. Moreover, the quasar forced a re-evaluation of cosmic power itself. The realization that matter falling into a supermassive black hole could unleash such enormous energy reshaped fundamental ideas about energy generation, gravity, and the behavior of matter under extreme conditions. Quasars like 3C273 serve as natural laboratories for physics at the limits, where relativistic speeds, magnetic fields, and intense gravitational forces converge. By studying these processes, astronomers gain insight not only into quasars themselves but also into the fundamental laws governing the universe. The broader implications extend beyond energy and distance. 3C273 transformed cosmology, providing one of the first compelling confirmations of the expanding universe and reinforcing the interpretation of redshift as a cosmological phenomenon. Its discovery catalyzed the search for thousands of other quasars, creating a new class of cosmic probes that illuminate the evolution of galaxies and the large-scale structure of the universe. Without 3C273, the study of supermassive black holes, relativistic jets, and galactic feedback would have developed much more slowly, and our understanding of the cosmos would remain far narrower. On a more philosophical level, 3C273 embodies the paradoxical beauty of the universe. It is at once tiny in appearance and colossal in power, remote in distance yet intimately connected to our quest for knowledge. It reminds us that appearances can be deceiving, that the universe holds extremes beyond our intuitive understanding, and that every discovery opens a pathway to further questions. The first quasar is not just an object in the sky, it is a testament to human curiosity, the power of observation, and the capacity of science to reveal truths that defy expectation. In reflecting on 3C273, one sees the broader arc of cosmic exploration, from the earliest radio surveys to multi-wavelength campaigns, from the development of theoretical models of black holes and jets to future observations with the James Webb Space Telescope and next-generation radio arrays. The quasar has served as both a guide and a challenge, a constant reminder that the universe is larger, more energetic, and more mysterious than even our most ambitious theories had imagined. Ultimately, the discovery of 3C273 was more than the identification of a single quasar. It was the unveiling of an entirely new realm of cosmic phenomena. It demonstrated that the universe harbors sources of energy so immense, processes so extreme, and distances so vast that they expand not only the horizons of science but also the imagination. By opening this window into the early universe and the extraordinary forces that shape it, 3C273 changed the way humanity views the cosmos, inspiring generations of astronomers and enthusiasts alike to explore the boundless, radiant, and mysterious expanse that surrounds us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.